when physics failed. Picture a piece of metal being heated in a forge. As the temperature rises, the metal begins to glow. First a dull red, then orange, then yellow, and, if heated sufficiently, a brilliant white. This is such a common observation that we barely think about it. Blacksmiths have known for millennia that color indicates temperature. What they didn't know, and what physicists at the end of the 19th century discovered to their horror, is that this simple phenomenon should be impossible. The problem goes by the rather technical name of black body radiation, though the concept is straightforward enough. A black body is simply an idealized object that absorbs all radiation falling on it and emits radiation based solely on its temperature. A cavity with a small hole approximates this nicely, or a piece of charcoal, or, for practical purposes, any dark object. When you heat such an object, it radiates energy across a spectrum of wavelengths. The question that tormented physicists was simple. How much energy should be emitted at each wavelength? Classical physics had a clear answer. Using well-established principles of thermodynamics and electromagnetism, physicists could calculate the expected spectrum, and the calculation was catastrophically wrong. According to classical theory, the amount of energy emitted should increase as wavelengths get shorter. Not just increase slightly, but increase without limit. As you moved from infrared to visible light to ultraviolet and beyond, the energy should climb toward infinity. The prediction was that any object at any temperature above absolute zero should emit infinite amounts of high-frequency radiation. Ovens should flood the room with lethal ultraviolet rays. The sun should instantly sterilize the solar system. Your own body, being warmer than its surroundings, should be emitting reality-destroying quantities of gamma rays. This prediction was so obviously wrong that physicists gave it a darkly humorous name, the ultraviolet catastrophe. And for several years at the end of the 1890s, no one could resolve it. The mathematics was checked and rechecked. The experiments were repeated with increasing precision. The discrepancy remained. Classical physics, the edifice built by Newton and Maxwell and Boltzmann, simply could not explain why a heated poker glows red instead of annihilating everything nearby. Enter Max Planck, a German physicist who was by his own admission a conservative man, deeply respectful of established theory. Planck was not looking to revolutionize physics. He was trying to save it. In 1900, working at the University of Berlin, Planck found a solution, though solution might be too generous a word. He found a mathematical trick that worked. Planck proposed something that seemed, even to him, absurd. What if energy wasn't continuous? What if, instead of being emitted in any arbitrary amount, electromagnetic energy could only be released in discrete packets in specific quantities that were multiples of some fundamental unit? He introduced a simple equation. E equals h times nu, where E is energy, nu is the frequency of the radiation, and h is a new constant of nature, now called Planck's constant. The value of h is tiny, about 6.626 times 10 to the negative 34 joule seconds, which is why we don't notice this quantization in everyday life. But at the scale of atoms and light, this discreteness matters enormously. With this assumption, with energy coming in packets rather than being continuous, Planck could derive a formula that perfectly matched the observed black body spectrum. The ultraviolet catastrophe disappeared. At high frequencies, where classical physics predicted infinite energy, Planck's formula correctly predicted a rapid drop-off. The curve matched experimental data beautifully. There was only one problem. Planck didn't believe it. He called his quantum hypothesis an act of desperation, and spent years trying to find a way to derive the same result without abandoning the sacred principle of continuous energy. He couldn't. Worse, other physicists largely ignored the result. It was seen as a useful mathematical tool, a calculation trick, not a statement about physical reality. Surely energy wasn't actually quantized. Surely this was just an approximation that happened to work. It would take 5 more years and a different problem entirely before anyone took Planck's quantum seriously. And the person who did it was not trying to support Planck. He was trying to understand something even stranger about light and metal. The photoelectric effect had been known since 1887, when Heinrich Hertz noticed something odd while experimenting with spark gaps. When ultraviolet light struck a metal surface, it caused the metal to emit electrons. This wasn't particularly surprising. Light carries energy, so it seemed reasonable that light could knock electrons loose. What was surprising were the details. Classical physics treated light as a wave, an oscillating electromagnetic field. If light was a wave, then brighter light should mean more energy, which should mean electrons ejected with higher speeds. It should be like ocean waves hitting a beach. Bigger waves should throw pebbles farther. This is not what happened. You could make the light as bright as you wanted, flooding the metal with intense illumination, and the electrons came out with exactly the same energy. The number of electrons increased, but their individual speeds did not. Then, if you changed the color of the light, if you increased its frequency even slightly, suddenly the electrons came out faster. Even dim violet light ejected electrons with more energy than brilliant red light. Stranger still, there was a threshold. Below a certain frequency, no electrons were emitted at all, no matter how bright you made the light. It was as if the electrons were refusing to respond unless the light met some minimum requirement. And that requirement had nothing to do with the light's intensity, and everything to do with its frequency. In 1905, a 26-year-old patent clerk in Bern named Albert Einstein published a paper that offered an explanation. It was one of 4 papers he published that year, any one of which would have secured his reputation. This particular paper, titled On a Heuristic Point of View Concerning the Production and Transformation of Light, would eventually win him the Nobel Prize. Not his work on relativity, which was too controversial, but this. Einstein took Planck's desperate mathematical trick and pushed it further. If energy is quantized when emitted, Einstein reasoned, perhaps light itself is quantized. Perhaps light doesn't just act like a wave. Perhaps it also consists of particles, discrete packets of energy that Planck's equation describes. These packets would later be called photons, though Einstein didn't use that term. Each photon, Einstein proposed, carries energy equal to h times nu, Planck's relation. When a photon strikes an electron in the metal, it delivers all of its energy at once, in a single quantum transaction. If that energy exceeds the work function, the amount needed to free the electron from the metal, the electron escapes. Any leftover energy becomes the electron's kinetic energy, its energy of motion. The equation is simple. The kinetic energy of the ejected electron equals h nu minus phi, where phi is the work function. Increase the frequency, You increase the photon energy and electrons come out faster. Decrease the frequency below the threshold, and even an infinite number of photons, brilliant light, won't eject a single electron, because no individual photon has enough energy to do the job. This explained everything. Why brightness didn't matter, only frequency. Why there was a sharp threshold. Why the relationship between frequency and electron energy was linear. The photoelectric effect wasn't evidence that light was a wave. It was evidence that light was, in some sense, made of particles. The physics community did not immediately embrace this idea. It seemed to contradict a century of evidence that light was a wave. Interference and diffraction patterns, the bending of light around obstacles, the way light from two sources could add together or cancel out, all of this screamed wave behavior. And now Einstein was claiming light was particles. It was deeply uncomfortable. Even to Einstein himself, who would spend much of his later career uncomfortable with the implications of quantum mechanics. But the photoelectric effect was just the beginning. There was still the problem of atoms, the problem that they existed at all. According to classical electromagnetism, an electron orbiting a nucleus should radiate energy continuously, like any accelerating charged particle must. An orbit is constant acceleration toward the center, even if speed is constant, so the electron should emit electromagnetic radiation. As it radiates, it loses energy. As it loses energy, it spirals inward. The calculation was straightforward and damning. Atoms should collapse in about 100 millionth of a billionth of a second. They don't. You are made of atoms that have existed for billions of years, stable, durable, unchanged. Classical physics could not explain why. In 1913, a young Danish physicist named Niels Bohr proposed a model of the hydrogen atom that was, by classical standards, nonsense. Bohr simply declared that certain orbits were allowed and others were not. Electrons could exist in these special orbits without radiating energy. The orbits were quantized, meaning only certain discrete values of angular momentum were permitted. Specifically, integer multiples of h, divided by 2 pi, a quantity now written as h bar. This was not derived from first principles. Bohr essentially imposed it by fiat because it gave the right answer. Electrons in these special orbits were stable. To jump from one orbit to another, an electron had to absorb or emit a photon with exactly the right energy to bridge the gap. If the electron dropped to a lower energy orbit, it emitted a photon. If it absorbed a photon with the right energy, it jumped to a higher orbit. This explained the spectral lines of hydrogen, the discrete colors of light that hydrogen emits when heated. For decades, scientists had known that hydrogen produced a specific pattern of lines, a kind of atomic fingerprint. A Swiss schoolteacher named Johann Balmer had even found an empirical formula that predicted the wavelengths of these lines, but no one knew why the formula worked. Bohr's model explained it. Each line corresponded to an electron jumping between two quantized orbits. The formula fell out naturally from the mathematics. It was a stunning success and deeply troubling. Bohr's model worked beautifully for hydrogen. It gave the right energy levels, the right spectral lines, even explained the size of the atom, about 1 angstrom in diameter. But it was built on an arbitrary postulate. Why were only certain orbits allowed? Bohr didn't know. He just knew that assuming they were quantized made the theory work, and the model failed for more complex atoms. helium with 2 electrons was already too complicated for Bohr's approach to handle accurately. The model was clearly incomplete, a stepping stone rather than a final theory. But it reinforced a disturbing pattern. Every time physicists fixed a problem by introducing quantization, by abandoning the classical assumption that physical quantities could vary continuously, the theory worked. And every time, it felt like a patch, not a principle. 3 separate problems: black body radiation, the photoelectric effect, and atomic stability, and 3 separate quantum solutions. Energy is quantized. Light is quantized. Atomic orbits are quantized. By the early 1920s, it was becoming clear that quantization wasn't a mathematical trick. It was a feature of reality. But no one yet understood what it meant or how to construct a coherent theory from these fragments. What was needed was a complete reformulation of mechanics itself, a new framework that could explain not just these specific phenomena, but all quantum behavior from first principles. That framework would emerge over the next few years, developed in 2 different forms by 2 very different physicists who would come to represent opposing philosophical views about the nature of reality. But before we get to Schrödinger's wave functions and Heisenberg's matrices, before we confront the measurement problem and the interpretations that still divide physicists today, we need to understand one more crucial piece of the puzzle. If light can behave like particles, can particles behave like waves? Black body radiation and Planck's desperate solution. Let's return to that glowing piece of metal, because the story of how physicists tried and failed to explain it reveals something important about how science progresses, or more accurately, how it doesn't. When you heat an object, any object, it emits electromagnetic radiation. At room temperature, this radiation is primarily in the infrared, which you can't see but can feel as heat. Raise the temperature, and the peak of emission shifts to higher frequencies. Around 800 Kelvin, about 500 degrees Celsius, objects begin to glow a dull red. At 1300 Kelvin, the glow shifts to orange. At 2000 Kelvin, yellow. At the temperature of the sun's surface, about 15800 Kelvin, the spectrum peaks in the visible range, which is not a coincidence. Our eyes evolved to detect the wavelengths our sun emits most strongly. This relationship between temperature and emitted light is so reliable that astronomers use it to determine the temperature of distant stars. An industrial pyrometer measures the temperature of molten metal in a foundry by analyzing the color of its glow. It's one of the most fundamental relationships in thermal physics, and in 1900, no one could explain it. The problem wasn't lack of trying. Some of the finest minds in physics had attacked black body radiation with the full arsenal of 19th century theoretical tools. The approach seemed straightforward enough. Inside a heated cavity, electromagnetic waves bounce around, reflecting off the walls. These waves form standing patterns, like the harmonics on a vibrating string. Each possible standing wave pattern is called a mode, and classical physics said that each mode should, on average, contain the same amount of energy, an amount determined by temperature. This idea, called the equipartition theorem, was a cornerstone of statistical mechanics. It had been tested and verified in countless other systems. There was no particular reason to doubt it for electromagnetic radiation. Except for one small problem. There are infinitely many modes. Or rather, the number of modes increases without limit as frequency increases. High-frequency modes with short wavelengths can fit many more standing wave patterns into a given volume than low-frequency modes. And if each mode gets the same energy, and there are infinitely many modes at high frequencies, then the total energy becomes infinite. This was the ultraviolet catastrophe, and it wasn't just wrong by a little. Classical physics predicted that a black body at any temperature should emit infinite power at high frequencies. Open your oven, and the universe should end. The theory didn't merely fail to match the data. It predicted something physically absurd. Several physicists proposed partial solutions. In 1896, Wilhelm Wien found an equation that worked well at high frequencies but failed at low frequencies. In 1900, Lord Rayleigh, and later James Jeans, derived what came to be called the Rayleigh-Jeans law, which worked perfectly at low frequencies but diverged to infinity at high frequencies, the catastrophe made explicit in mathematical form. The experimental data, meanwhile, was unambiguous. Black body radiation has a characteristic curve. At low frequencies, intensity increases with frequency. At some point, determined by temperature, the intensity reaches a peak. Beyond that peak, intensity drops off rapidly at higher frequencies. There's no catastrophe, no divergence, just a smooth curve with a well-defined maximum. Max Planck had been working on this problem for years. Born in 1858 in Kiel, Germany, Planck had been discouraged from studying physics by his professor, who told him that the field was essentially complete, with nothing fundamental left to discover. Fortunately for physics, Planck ignored this advice. By 1900, he was working at the University of Berlin and had become somewhat obsessed with black body radiation. Planck's approach was initially thermodynamic. He tried to understand the entropy of radiation, how disorder and energy related in electromagnetic fields. He made progress, finding relationships that seemed to work, but he couldn't derive them from first principles. They were, in a sense, educated guesses that fit the data. On October 19, 1900, Planck presented a new formula at a meeting of the German Physical Society. It was empirical, constructed to fit experimental measurements rather than derived from theory. But it worked. Across the entire spectrum, at all temperatures. Planck's formula matched the observed black body curve perfectly. Within a few weeks, experimentalists confirmed the formula's accuracy with extraordinary precision. The formula worked. The question was why? What physical principle could produce this mathematical relationship? Planck spent 2 months in what he later described as the most intense work of his life, trying to derive his formula from fundamental physics. The breakthrough, when it came, required what he considered a violation of everything he'd been taught about the continuity of nature. On December 14, 1900, Planck presented his derivation. The key assumption was radical. He proposed that the energy of oscillators in the cavity walls, the charged particles that absorbed and emitted radiation, could not take on any arbitrary value. Instead, energy was quantized. An oscillator of frequency nu could only have energies that were integer multiples of h times nu, where h was a new constant, a fundamental quantity that determined the size of these energy packets. The value of h is approximately 6.626 times 10 to the negative 34 joule-seconds. This number, now called Planck's constant, is unimaginably small by everyday standards. To put it in perspective, If you lift a single grain of sand 1 millimeter, you've changed its potential energy by trillions upon trillions of times h. At human scales, energy appears continuous because the fundamental quantum is so tiny that we can't perceive the steps. But at the scale of atoms and individual electromagnetic oscillations, h matters. When an atom absorbs or emits light, the energy change is comparable to h times the frequency of that light. The granularity of energy becomes relevant. With this quantization assumption, Planck could rederive his black body formula from first principles. The ultraviolet catastrophe disappeared. At high frequencies, the energy per quantum, HA nu, becomes very large. To excite a high-frequency mode requires a substantial amount of energy in a single quantum leap. At any finite temperature, the probability of having enough thermal energy available to excite these high-frequency modes drops exponentially. Most high-frequency modes simply aren't populated. They contribute nothing to the emitted radiation. The black body curve is thus a kind of census of which quantum modes are thermally accessible at a given temperature. Low-frequency quanta with small energy are easily excited. High-frequency quanta with large energy are rare. The peak of the curve occurs where these competing factors balance. It was an elegant solution. It worked mathematically and explained the experimental observations perfectly. Planck should have been triumphant. He wasn't. He was horrified. In later years, Planck described his quantum hypothesis as an act of desperation. He was a conservative physicist, trained in the classical tradition, deeply committed to the continuity of physical processes. The idea that energy came in discrete lumps contradicted everything he believed about nature. Planck spent the next several years trying to eliminate the quantum hypothesis, to find some way to derive his formula without abandoning continuous energy. He explored various mathematical approaches, consulted with colleagues, attacked the problem from different angles. Nothing worked. Every path back to classical physics led back to the ultraviolet catastrophe. What made this particularly frustrating was the limited scope of the quantum assumption. Planck had quantized the energy of the oscillators in the cavity walls, not the electromagnetic field itself. He viewed quantization as a property of matter, of how atoms absorbed and emitted radiation, not as a property of light. Light itself, he believed, was still a continuous wave. This might seem like a subtle distinction, but it was philosophically important to Planck. If quantization applied only to matter, perhaps it could be explained eventually by some deeper classical mechanism. Perhaps atoms had some internal structure that forced them to interact with light in discrete amounts. The fundamental continuity of nature could be preserved. The physics community's initial response was muted. Planck's formula was accepted because it worked. The quantum hypothesis behind it was largely ignored. Most physicists treated h as a useful mathematical parameter, rather than evidence of fundamental granularity in nature. The implications were too strange, too at odds with established physics, to be taken seriously without more evidence. That evidence would come, but not from thermal radiation. It would come from Einstein's analysis of the photoelectric effect, where the quantum nature of light itself could no longer be avoided. And it would come from Bohr's model of the atom, where quantization appeared in a completely different context, suggesting that this wasn't a peculiarity of how matter interacted with light, but a fundamental feature of microscopic systems. But in 1900, none of this was yet clear. Planck had solved the black body problem, but in doing so, he'd opened a door he wished had remained closed. He'd introduced a fundamental constant of nature, H, that measured the graininess of reality at small scales. And, though he couldn't have known it at the time, that constant would appear again and again in every corner of quantum mechanics. Planck's constant sets the scale at which quantum effects become important. It determines the wavelength of matter waves, the magnitude of uncertainty relations, the spacing of energy levels in atoms, and the rate at which quantum systems evolve. It appears in the Schrödinger equation, in Heisenberg's uncertainty principle, in the commutation relations of quantum operators. Every quantum phenomenon, from the stability of atoms to the operation of transistors to the decay of radioactive nuclei, involves H. In a sense, Planck's constant measures how different the quantum world is from the classical world. If H were zero, quantum mechanics would collapse into classical mechanics. Energy would be truly continuous. Particles would have definite positions and momenta simultaneously. The universe would behave the way our intuitions, trained on everyday objects, expect it to. But H is not zero. It's small, almost incomprehensibly small, but it's finite. And that makes all the difference. It means there's a fundamental limit to how finely nature can be divided, how precisely things can be measured, how continuously systems can evolve. Reality has a grain size, and Planck reluctantly, accidentally, found it. The photoelectric effect in light particles. In 1887, Heinrich Hertz was conducting experiments to prove the existence of electromagnetic waves. The ripples in electric and magnetic fields that James Clerk Maxwell had predicted 2 decades earlier. Hertz built a device called a spark gap transmitter, essentially 2 metal spheres separated by a small air gap. When charged to high voltage, a spark would jump across the gap, generating electromagnetic waves that could be detected by a receiver across the room. During these experiments, Hertz noticed something odd. When ultraviolet light shone on the metal electrodes, sparks jumped more readily. The presence of light somehow made it easier for electricity to flow. This seemed curious but not particularly profound. Hertz noted the effect, published it, and moved on. He had, after all, just confirmed Maxwell's theory and proven the existence of radio waves. The strange behavior of light on metal seemed like a minor footnote. It wasn't. What Hertz had stumbled upon without recognizing its significance was the photoelectric effect, and explaining it would require abandoning the wave theory of light that Hertz himself had just triumphantly confirmed. Over the next 2 decades, physicists studied the photoelectric effect in detail. The basic phenomenon was simple enough. Shine light on certain metals, particularly alkali metals like sodium or potassium, and electrons are ejected from the surface. You could collect these electrons, measure their charge and mass, verify they were the same particles J.J. Thomson had discovered in cathode rays. Light was knocking electrons out of metal. The question was how. The experimental observations revealed a pattern that made no sense within the framework of wave theory. Classical physics treated light as an oscillating electromagnetic field, a continuous wave that carried energy. When this wave struck a metal surface, the oscillating electric field should shake the electrons. given enough time and enough intensity, these oscillations should impart sufficient energy to eject electrons from the metal. This led to clear predictions. First, brighter light, meaning more intense electromagnetic fields, should eject electrons with higher kinetic energy. Second, the frequency of the light. Its color shouldn't matter much. Any frequency should work if the light was bright enough. Third, there should be a time delay between when light first strikes the surface and when electrons emerge. As the electrons gradually accumulate energy from the wave. Every single one of these predictions was wrong. Brighter light did not increase the energy of ejected electrons. You could flood a metal surface with intense red light, brilliant enough to hurt your eyes, and the electrons that emerged, if any emerged at all, came out with exactly the same energy as they would from dim red light. Brightness affected only the number of electrons ejected, not their individual energies. Frequency, meanwhile, mattered enormously. Each metal had a threshold frequency, a minimum color requirement. Below this threshold, no electrons were emitted regardless of intensity. Shine infrared light, no matter how bright, on a piece of sodium, and nothing happens. Increase the frequency just slightly into the visible range, and suddenly electrons start flowing, even if the light is dim. Above the threshold, there was a precise relationship. Increase the frequency, and electrons came out faster with more kinetic energy. The relationship was linear. Doubling the frequency didn't quite double the electron energy, but increased it by a fixed amount for each unit increase in frequency. And there was no time delay, not even a microsecond. The moment light above the threshold frequency struck the metal, electrons were emitted. There was no gradual accumulation of energy, no warming up period. The response was instantaneous. Wave theory couldn't explain any of this. If light was a continuous wave spreading its energy over the metal surface, how could a single electron suddenly acquire enough energy to escape? It would be like expecting a gentle, widespread rainfall to somehow launch individual droplets of water violently into the air. The energy distribution was all wrong. In 1905, Albert Einstein published a paper in the journal Annalen der Physik. He was 26 years old, working as a technical expert third class at the Swiss Patent Office in Bern, having failed to secure an academic position after completing his doctorate. That year, 1905, would later be called his Annus Mirabilis, his miracle year. He published 4 papers, each revolutionary in its own right. One paper explained Brownian motion, the random jittering of pollen grains suspended in water, providing compelling evidence for the atomic nature of matter. Another introduced the special theory of relativity, overturning Newtonian concepts of absolute space and time. A third derived the equivalence of mass and energy, E equals mc squared, perhaps the most famous equation in physics. But it was the 4th paper, on the photoelectric effect, that won Einstein the Nobel Prize in 1921. Not relativity, which was still considered too controversial and insufficiently verified. Not mass-energy equivalence, which seemed more mathematical than physical. The photoelectric effect, because it could be tested directly, and because it revealed something fundamental about the nature of light. Einstein's paper was titled, "On a Heuristic Point of View Concerning the Production and Transformation of Light." The word heuristic is important. Einstein was proposing not a complete theory, but a useful way of thinking about light that might resolve certain paradoxes. He was being careful, tentative even, though the implications of his proposal were radical. Einstein took Planck's quantum hypothesis seriously, more seriously than Planck himself did. If electromagnetic oscillators could only emit and absorb energy in discrete amounts, Einstein reasoned, perhaps light itself traveled through space in discrete packets. Perhaps the electromagnetic field wasn't continuously distributed, but rather consisted of particle-like quanta, each carrying energy equal to h times nu, Planck's relation. These light quanta, later named photons by the chemist Gilbert Lewis in 1926, behaved in some ways like particles. Each photon carried a definite amount of energy determined by its frequency. When a photon struck an electron in the metal, it delivered all of its energy in a single, localized interaction. This was not a wave gently shaking an electron over time. This was a collision, a quantum transaction where energy transferred instantaneously and completely. The electron, absorbing this energy, could use it to escape the metal, but escaping required work. The electron was bound to the metal by attractive forces, held in place by the positive charges of the atomic nuclei. Breaking free required a minimum amount of energy, called the work function, denoted by the Greek letter phi. Different metals have different work functions depending on how tightly they bind their electrons. If the photon's energy, h nu, exceeded the work function phi, the electron could escape. Any leftover energy became the electron's kinetic energy, its energy of motion. The equation was simple and exact. Kinetic energy equals h nu minus phi. This explained everything. Why frequency mattered. A low-frequency photon, even from intense light consisting of many such photons, simply didn't carry enough energy per quantum to overcome the work function. No individual photon could free an electron, so no electrons escaped. Increase the frequency past the threshold, and suddenly each photon had enough energy. Even a single photon could now eject an electron. Why brightness didn't affect electron energy. Brightness meant more photons, not more energetic photons. More photons meant more electrons ejected, but each electron received energy from a single photon, so each emerged with the same energy. Why there was no time delay. The interaction was a single quantum event, a photon absorbed by a single electron in a single instant. There was no accumulation process, no gradual buildup. Either the photon had enough energy or it didn't. If it did, the electron left immediately. And why the relationship between frequency and kinetic energy was linear. If you plotted electron energy against light frequency, you got a straight line with slope h and y-intercept negative phi. You could measure Planck's constant directly from the photoelectric effect, and the value agreed with the one Planck had extracted from black body radiation. The same h appeared in both phenomena. Einstein's proposal was met with skepticism bordering on disbelief. The wave theory of light was not some speculative hypothesis. It was backed by a century of experimental evidence. Interference patterns, where two light beams could combine to create regions of brightness and darkness. Diffraction, where light bent around obstacles in ways that only waves could. Polarization, where light exhibited orientation effects consistent with transverse waves. Thomas Young's double-slit experiment in 1801 had seemingly proven beyond doubt that light was a wave. If you shone light through two narrow slits, you saw an interference pattern on a screen behind them, alternating bright and dark bands. This was exactly what you'd expect from waves spreading out from each slit and interfering with each other. Particles couldn't do this. Particles would go through one slit or the other and pile up in two clusters. And now, Einstein was claiming light consisted of particles. How could particles produce interference patterns? How could a photon go through two slits at once? Einstein didn't have good answers to these questions. He acknowledged the problem explicitly in his paper. Light exhibited both wave and particle properties. In some experiments, particularly those involving interference and diffraction, light behaved as a wave. In others, particularly the photoelectric effect, light behaved as particles. This was paradoxical, perhaps even contradictory, but it seemed to be what nature demanded. The physics community resisted this conclusion for years. Even after Robert Millikan performed meticulous experiments between 1914 and 1916 that confirmed Einstein's photoelectric equation with high precision, Millikan himself didn't accept the photon hypothesis. He thought there must be some other explanation that preserved the wave nature of light. There wasn't. Gradually, as more evidence accumulated, particularly from Compton scattering experiments in 1923, where X-rays bounced off electrons like billiard balls, the particle nature of light became undeniable. Light was, in some sense, both wave and particle. Not sometimes one and sometimes the other, but somehow both at once, exhibiting different aspects depending on how you measured it. This was the beginning of wave-particle duality, one of the central mysteries of quantum mechanics. But if light, which everyone thought was obviously a wave, could behave like particles, a natural question arose. Could particles, which everyone thought were obviously particles, behave like waves? Atomic spectra and Bohr's model. If you heat a gas until it glows, perhaps by running an electric current through it, the light it emits is not like the light from a heated solid. A hot piece of iron glows with a continuous spectrum, all colors blending together. A hot gas produces something stranger, discrete lines of color separated by darkness. Each element has its own pattern, a kind of optical fingerprint. Sodium vapor lamps, common in older street lighting, emit a characteristic yellow-orange glow. Look at that light through a spectroscope, and you'll see it's not really yellow-orange, but two very specific wavelengths of yellow light close together. Neon signs glow red, but the red comes from specific discrete wavelengths, not a continuous range. Hydrogen, the simplest element, produces four visible lines: red, cyan, blue, and violet. These spectral lines had been known since the early 1800s, when Joseph von Fraunhofer discovered dark lines in the sun's spectrum, absorption lines where specific wavelengths were missing. Later, physicists realized that hot gases emit light at the same specific wavelengths where cool gases absorb light. Every element had its signature pattern. In 1885, a Swiss schoolteacher named Johann Balmer, working with no particular theoretical framework, found an empirical formula that predicted the wavelengths of hydrogen's visible spectral lines. The formula was purely numerical, a mathematical pattern with no physical justification. It worked because it worked. Balmer himself wrote that he had no idea why nature followed this particular mathematical relationship. Others extended the pattern. Johannes Rydberg generalized Balmer's formula to cover not just visible light but all spectral lines of hydrogen, including those in the ultraviolet and infrared. The Rydberg formula contained a constant now called the Rydberg constant, with a value of about 1.097 times 10 to the 7th per meter. Like Balmer's formula, it was empirical, a description without explanation. This was the situation in 1913 when Niels Bohr arrived in Manchester to work with Ernest Rutherford. Bohr was 28, fresh from his doctorate in Copenhagen, and Rutherford had recently discovered the atomic nucleus. 2 years earlier, Rutherford had fired alpha particles at gold foil and found that atoms were mostly empty space with a tiny, dense, positively charged nucleus at the center. Electrons somehow orbited this nucleus. The problem was that they shouldn't. An electron moving in a circle is accelerating, constantly changing direction even if its speed stays constant. And, according to Maxwell's equations, any accelerating charged particle must radiate electromagnetic energy. An orbiting electron should emit light continuously, losing energy as it does so. As it loses energy, the orbit should decay, spiraling inward. The calculation was straightforward and catastrophic. Atoms should collapse in about 10 to the negative 11 seconds, a tenth of a trillionth of a second. This was not a minor discrepancy. This was classical physics predicting that matter, all matter, including you and the chair you're sitting on, should have collapsed into a shower of radiation before the universe was even microseconds old. The fact that you exist to hear this is proof that classical physics was fundamentally wrong about atoms. Bohr's solution was audacious. He simply declared that certain orbits were special, that electrons in these particular orbits did not radiate energy. This was not derived from Maxwell's equations or Newton's laws. It contradicted them. Bohr was imposing a new rule on nature. Certain states are stable, not because classical physics says they should be, but because they are. Which orbits were special? Bohr proposed that angular momentum, the rotational equivalent of linear momentum, was quantized. An electron could only have angular momentum values that were integer multiples of h divided by 2p, the quantity now written as h bar and pronounced h bar. So, angular momentum could be or 2 or 3, but nothing in between. This immediately gave specific allowed orbits. The electron in hydrogen's ground state, its lowest energy state, had angular momentum and orbited at a specific radius, about 53 angstroms, now called the Bohr radius. Higher energy states had larger orbits with angular momentum 2, 3, and so on. Each orbit had a definite energy. The ground state, with the smallest orbit, had the lowest energy, about negative 13.6 electron volts, where negative means the electron is bound to the nucleus. Higher orbits had higher, less negative energies. The energy of the nth orbit was proportional to negative 1 over n squared, where n is the principal quantum number, the integer counting which orbit you're in. When an electron jumped from a higher orbit to a lower one, it emitted a photon. The photon's energy exactly equaled the difference in orbital energies. Since energy levels were quantized, the photon energies were quantized, which meant the wavelengths were quantized, which explained the discrete spectral lines. Bohr could now derive the Rydberg formula from first principles. The wavelengths of spectral lines corresponded to electrons dropping from one orbit to another. The visible lines Balmer had found came from electrons falling to the n-2 orbit from higher orbits. Ultraviolet lines came from transitions down to n-1. Infrared lines came from transitions down to n-3 or higher. Every spectral line corresponded to a specific orbital jump. The agreement with experiment was spectacular. Bohr's model predicted the Rydberg constant from fundamental constants, the electron mass, the elementary charge, Planck's constant, and the permittivity of free space. Plug in the known values, and out came the Rydberg constant, accurate to several decimal places. The model also predicted the size of hydrogen atoms, the ionization energy required to remove an electron, and the existence of spectral lines that hadn't yet been observed but were found shortly after. It was one of the great triumphs of early quantum theory, but it was also deeply unsatisfying. Bohr had not explained why angular momentum was quantized. He had simply imposed it as a postulate because it gave the right answer. The model was a mixture of classical and quantum ideas, electrons following classical orbits but with quantum restrictions. And it only worked for hydrogen. Helium with 2 electrons was already too complicated. The mutual repulsion between the 2 electrons, both negatively charged, made the mathematics intractable within Bohr's framework. For heavier atoms, the situation was hopeless. The model could make rough predictions, but couldn't handle the complexity of multiple interacting electrons. There was also the question of what happened during a quantum jump. An electron in one orbit disappeared and reappeared in another orbit, emitting a photon in the process. But what happened in between? Did the electron pass through the intervening space? If so, how? Its energy in that intermediate region didn't correspond to any allowed state. If not, if it simply vanished from one place and appeared in another, what did that even mean? Bohr himself was troubled by these questions. He introduced the correspondence principle, the idea that quantum mechanics should reduce to classical mechanics in some limit, typically for large quantum numbers or large systems. At very high orbits, far from the nucleus, the energy spacing between adjacent levels becomes small, and the electron's behavior should start to resemble classical orbits. This was a useful guiding principle, but not a complete theory. What was needed was a deeper framework, one that didn't simply paste quantum restrictions onto classical orbits, but derived quantum behavior from fundamental principles. The question was what those principles might be. In 1923, a French doctoral student named Louis de Broglie proposed something that seemed obvious in hindsight but was radical at the time. Einstein had shown that light, traditionally thought to be waves, had particle properties. De Broglie asked, if waves can behave like particles, can particles behave like waves? De Broglie suggested that all matter, not just light, had an associated wavelength. For a particle with momentum p, the wavelength L should be h divided by p, a direct parallel to the relationship for photons. This was a bold claim. Electrons, atoms, even baseballs should exhibit wave behavior under the right circumstances. For everyday objects, the de Broglie wavelength is absurdly small. A baseball moving at 40 meters per second has a wavelength of about 10 to the negative 34 meters, far smaller than any atomic nucleus. You will never observe the wave nature of a baseball because its wavelength is inaccessibly small. But for electrons, with their tiny mass, the de Broglie wavelength at typical speeds is comparable to atomic sizes, about an angstrom or so. At this scale, wave behavior should be detectable, and suddenly, Bohr's quantization condition made sense. If an electron in an orbit is a wave, specifically a wave wrapped around a circle, the wave must connect smoothly with itself. The circumference of the orbit must be an integer number of wavelengths. If it's not, the wave interferes destructively with itself and cancels out. Only orbits where the circumference equals n wavelengths are stable. This condition, that the circumference equals n times Al, is mathematically equivalent to Bohr's quantization of angular momentum. De Broglie had provided a physical picture for why only certain orbits exist. They're the ones where the electron wave fits evenly around the circle. Within a few years, experiments confirmed matter waves directly. In 1927, Clinton Davison and Lester Germer, working at Bell Labs, fired electrons at a nickel crystal and observed diffraction patterns, the same kind of interference effects that waves produce. Electrons weren't just acting like waves. They were producing the signature patterns that only waves could create. George Paget Thomson, son of J.J. Thomson, who had discovered the electron, performed similar experiments and found the same results. There was a certain poetry to this. The father had proven the electron was a particle, and the son had proven it was a wave. Both were correct. The wave nature of matter was real and measurable, but it raised profound questions. What exactly was waving? An electron is a particle with a definite charge and mass. What physical quantity was oscillating to create a wave? And if particles were waves spread out in space, how could they leave point-like tracks in detectors? These questions would lead to the full development of quantum mechanics, to Schrödinger's wave equation, and Heisenberg's matrix mechanics, to the probabilistic interpretation and the measurement problem. But before we get there, we need to confront something even stranger than wave-particle duality. We need to understand uncertainty, not as a limitation of measurement, but as a fundamental feature of reality itself. De Broglie and wave-particle duality. Louis de Broglie came from an aristocratic French family with a tradition of military service. His older brother Maurice was a physicist who studied X-rays, and Louis initially pursued history before switching to physics, partly under his brother's influence. By 1923, at age 31, he was working on his doctoral thesis at the Sorbonne in Paris. De Broglie had been thinking about the strange dual nature of light. Einstein's photons behaved like particles in some experiments, yet light still produced interference patterns that only waves could explain. There was also a curious asymmetry in physics. Light, which everyone had thought was waves, turned out to have particle properties. But matter, electrons, and atoms and such was still understood purely as particles. Nature seemed lopsided. De Broglie proposed restoring symmetry. If wave-like light could behave as particles, perhaps particle-like matter could behave as waves. The logic was almost aesthetic, a sense that nature should be balanced. But de Broglie went further than philosophical symmetry. He derived a specific relationship. For photons, Einstein had established that energy equals h times frequency. From relativity, energy also equals momentum, times the speed of light for massless particles. Combining these relationships gave momentum equals h divided by wavelength. De Broglie simply extended this to matter. Any particle with momentum p should have an associated wavelength OL equal to h divided by p. This was his entire thesis. One central idea explored from various angles, but essentially this single relationship. Particles have wavelengths inversely proportional to their momentum. Fast particles have short wavelengths. Slow particles have long wavelengths. Heavy particles, with large momentum at any given speed, have shorter wavelengths than light particles moving at the same speed. The thesis committee was uncertain. Einstein, reviewing the work, found it interesting and potentially significant. That endorsement was enough. De Broglie received his doctorate, and his hypothesis entered the physics literature as a curious speculation. For a baseball, say one with mass 0.145 kilograms moving at 40 meters per second, the de Broglie wavelength works out to about 10 to the negative 34 meters. This is roughly 20 orders of magnitude smaller than a proton. You could never, under any circumstances, observe wave behavior from a baseball. The wavelength is too small to interact with anything, too small to produce measurable interference or diffraction. But for an electron, the calculation changes dramatically. An electron has a mass of about 9.11 times 10 to the negative 31 kilograms. At a modest speed of, say, 2,000 meters per second, the de Broglie wavelength is about 0.36 nanometers, roughly the spacing between atoms in a crystal. At this scale, wave behavior becomes relevant and potentially observable. The question was how to test it. You can't just shine electrons at a wall and expect to see anything interesting. To observe wave behavior, you need the right geometry, a setup where waves would produce distinctive patterns that particles wouldn't. The classic demonstration of wave behavior is diffraction, where waves bend around obstacles or spread out after passing through small openings. In 1927, Clinton Davison and Lester Germer, working at Bell Telephone Laboratories in New York, were studying how electrons scattered off nickel surfaces. This wasn't originally meant to test de Broglie's hypothesis. They were investigating the structure of nickel for practical purposes related to vacuum tube technology. Their experiment involved firing a beam of electrons at a nickel target and measuring how many electrons scattered in different directions. Initially, the results were unremarkable. Then, by accident, their vacuum system failed. Air rushed in, and the nickel sample oxidized. To clean it, they heated the sample in a hydrogen atmosphere. This heating had an unintended consequence. The nickel, initially a polycrystalline material with small, randomly oriented crystal grains, annealed into larger, more ordered crystals. When Davison and Germer resumed their experiments, the scattering pattern had changed completely. Instead of a smooth distribution, they now saw sharp peaks in intensity at specific angles. It took them some time to realize what they were seeing. The electrons were diffracting off the regular lattice of atoms in the nickel crystal, exactly like X-rays had been shown to diffract in similar experiments. The nickel crystal was acting as a three-dimensional diffraction grating for the electron waves. The angles of the intensity peaks matched precisely the predictions from de Broglie's wavelength formula. Electrons were behaving as waves, not metaphorically, not approximately. They were producing the same diffraction patterns that light produces when passing through gratings or bouncing off crystals. At around the same time, George Paget Thomson, working at the University of Aberdeen in Scotland, was performing similar experiments using a different technique. He fired electrons through thin metal foils and observed the pattern on a screen behind the foil. Instead of a simple shadow or a scattered blur, he saw concentric rings, a classic diffraction pattern. The irony was rich. Thomson's father, J.J. Thomson, had won the Nobel Prize in 1906 for proving the electron was a particle, showing it had definite charge and mass and could be deflected by electric and magnetic fields. Now, his son had won the Nobel Prize in 1937, shared with Davison, for proving the electron was a wave. Both were right. The electron is genuinely both. This wasn't a matter of perspective or experimental setup or philosophical interpretation. In some experiments, electrons behave as discrete particles. They arrive at detectors in localized spots, carry definite momentum, leave tracks in cloud chambers. In other experiments, electrons behave as extended waves. They produce interference patterns, diffract around obstacles, exhibit wave-like spreading. The natural question is which one the electron really is. The answer appears to be neither or both, or that the question itself is wrong. An electron is not a tiny ball that sometimes pretends to be a wave. It's not a wave that sometimes clumps up like a particle. It's something else. Something that exhibits particle-like properties under certain conditions and wave-like properties under others. This is wave-particle duality, and it applies to everything, not just electrons and photons. Neutrons diffract. Atoms diffract. In 1999, researchers in Austria observed interference patterns from buckyballs, molecules of 60 carbon atoms shaped like soccer balls. In 2019, interference was demonstrated with molecules containing over 2,000 atoms. As objects get larger, the wave behavior becomes harder to observe. The de Broglie wavelength shrinks. Environmental interactions, stray photons, air molecules, vibrations, all tend to destroy the delicate phase relationships needed for interference. But the wave nature doesn't disappear. It's still there, just increasingly difficult to isolate. The most famous demonstration of wave-particle duality remains the double-slit experiment. Take a source of electrons, or photons, or atoms. Fire them one at a time at a barrier with two narrow slits. Place a detector screen behind the barrier. What do you see? If electrons were classical particles, they'd go through one slit or the other and pile up in two clusters on the screen. That's not what happens. Instead, you get an interference pattern, alternating bands of high and low intensity. The electrons are somehow going through both slits, interfering with themselves, and producing a wave pattern. You can try to catch the electron in the act to see which slit it goes through. Put detectors at the slits to record which path each electron takes. The moment you do this, the interference pattern disappears. You now see two clusters, like you'd expect from classical particles. The act of determining which slit the electron went through destroys the wave behavior. This isn't because the detector disturbs the electron physically, though early explanations sometimes suggested that. You can use very gentle detection methods, so-called quantum non-demolition measurements. The interference pattern still vanishes. The issue is more fundamental. When you have information about which path the electron took, even in principle, even if you don't actually look at that information, the interference is destroyed. Niels Bohr called this complementarity. Wave and particle properties are complementary aspects of quantum objects. You can observe one or the other, but not both simultaneously. Set up an experiment to see particle behavior, and that's what you'll see. Set up an experiment to see wave behavior, and that's what you'll observe. But you cannot set up an experiment that reveals both aspects at once. This led to the notion of measurement in quantum mechanics, which turns out to be far more problematic than anyone in the 1920s initially realized. When you measure something, you're not just passively observing a pre-existing property. You're interacting with the system in a way that forces it to exhibit one aspect of its nature rather than another. Before measurement, the electron isn't secretly going through one slit or the other while you're not looking. It's not going through both slits simultaneously in some spatial sense. It exists in a state called superposition, where it genuinely has both possibilities available, and the measurement process selects which one becomes actual. This is deeply strange. We are used to thinking that objects have definite properties whether we look at them or not. A book on a shelf is in a specific location whether you check or not. An electron passing through a double slit does not have a definite path until you measure which slit it went through. Before measurement, the path is fundamentally undefined, not unknown, but undefined. De Broglie himself was never entirely comfortable with this interpretation. He preferred pilot wave theory, where particles have definite positions at all times but are guided by an accompanying wave field. This removes some of the strangeness, but at a cost. The wave field has to be non-local, connecting distant parts of the system instantaneously, and the theory makes exactly the same predictions as standard quantum mechanics for any experiment you can actually perform. Wave-particle duality remains conceptually challenging nearly a century after its discovery. We've learned to calculate with it, to predict experimental outcomes with extraordinary precision. But what it means, what's actually happening when an electron produces an interference pattern, remains genuinely puzzling. And it's about to get worse, because wave-particle duality is just the beginning of quantum strangeness. Next comes uncertainty. The uncertainty principle. In 1927, Werner Heisenberg was 25 years old and suffering from hay fever. To escape the pollen-heavy air of Copenhagen, where he was working with Niels Bohr, he traveled to the island of Heligoland in the North Sea. There, alone and isolated, he worked through a problem that had been troubling him for months. Heisenberg had been developing a new formulation of quantum mechanics based on matrices, mathematical objects that represented observable quantities like position and momentum. What struck him was that these matrices didn't commute. In ordinary arithmetic, the order of multiplication doesn't matter. 3 times 5 equals 5 times 3. But matrix multiplication is different. The order matters. Matrix A times matrix B generally does not equal matrix B times matrix A. For position and momentum specifically, Heisenberg found a precise relationship. If you multiply the position matrix by the momentum matrix and subtract the result of multiplying them in the opposite order, you don't get 0. You get I times h bar, where I is the square root of -1, and h bar is Planck's constant divided by 2p. This mathematical fact, written as a commutation relation, seemed abstract, but Heisenberg realized it had a profound physical consequence. You cannot simultaneously measure position and momentum with arbitrary precision. The more accurately you determine one, the less accurately you can know the other. This wasn't a statement about measurement technology or experimental skill. It was a fundamental limit imposed by nature itself. The relationship is usually written as dx/dp. 2. Where dx represents the uncertainty in position and dp represents the uncertainty in momentum. The product of these uncertainties cannot be smaller than h bar divided by 2. If you reduce the position uncertainty, the momentum uncertainty must increase to compensate. If you pin down the momentum precisely, the position becomes completely indefinite. This is the Heisenberg uncertainty principle, and it's one of the most misunderstood concepts in physics. The common explanation, repeated in countless textbooks, is that measuring position disturbs the particle's momentum, or vice versa, so precise measurement of both becomes impossible. This explanation is wrong, or at least deeply misleading. The uncertainty principle is not about measurement disturbing the system. You can imagine hypothetical measurements that are arbitrarily gentle, that barely touch the particle at all. The uncertainty persists. It's not about the limitations of measuring devices or the skill of experimenters. It's about what properties a quantum particle actually has. An electron does not have a definite position and a definite momentum simultaneously. Not because we can't measure both, but because both don't exist simultaneously. Before measurement, the electron genuinely doesn't have a precise position and momentum. These properties are fundamentally fuzzy, spread out, indefinite. The uncertainty principle quantifies how fuzzy they must be. This might sound like philosophical wordplay, but it has concrete consequences. Consider an electron confined to a small region of space, trapped in a box perhaps. The uncertainty in its position is limited by the size of the box. If the box is 1 nanometer across, dx is about 1 nanometer. The uncertainty principle then demands that dp must be at least divided by twice dx, which works out to about 10 to the negative 25 kilogram meters per second. This uncertainty in momentum translates to kinetic energy. The electron must have at least some motion, some kinetic energy, just to satisfy the uncertainty principle. This is called zero-point energy. Even at absolute zero temperature, even in the lowest possible energy state, quantum particles retain kinetic energy, because being completely at rest would violate the uncertainty principle. This zero-point energy explains why liquid helium doesn't freeze at atmospheric pressure, no matter how cold you make it. Helium atoms are light, so their zero-point motion is significant. The kinetic energy from this motion is enough to overcome the weak attractive forces between helium atoms. They jiggle too much to lock into a solid crystal structure. You need to apply pressure to constrain their position more tightly and thus allow the attractive forces to dominate before helium will solidify. Zero-point energy also explains the size of atoms. An electron close to the nucleus has small position uncertainty, which means large momentum uncertainty, which means high kinetic energy. An electron far from the nucleus has low kinetic energy but high potential energy due to the attractive electric force. The actual orbit is a balance between these effects. The atom settles into a size where the total energy, kinetic plus potential, is minimized. Without the uncertainty principle, without zero-point energy, electrons would fall into the nucleus and atoms would collapse. There's also a time-energy uncertainty principle, though it's subtly different from the position-momentum version. dE dt 2, where dE is uncertainty in energy and dt is the time interval over which you're measuring. This relationship is often stated less carefully, which leads to confusion. But one valid interpretation is that short-lived quantum states have inherently uncertain energies. Particles can exist in states that aren't energy eigenstates, states with definite energy. If a particle is in a superposition of different energy states, measuring its energy at different times will give different results. The spread in these results is dE. The time-energy uncertainty principle limits how quickly this energy can be determined. One consequence is that virtual particles can briefly violate energy conservation, borrowing energy from the vacuum as long as they pay it back within a time interval set by the uncertainty principle. An electron can emit and reabsorb a photon, even if the electron doesn't have enough energy to create that photon, as long as the photon exists only briefly. These virtual processes contribute to measurable effects like the Lamb shift and the anomalous magnetic moment of the electron. Tiny corrections to simple predictions that have been verified to extraordinary precision. The uncertainty principle also applies to other pairs of variables, angular position and angular momentum, for instance. If you know precisely which direction a particle is spinning, you cannot know the magnitude of that spin with arbitrary precision in other directions. This is why measuring spin along one axis destroys information about spin along perpendicular axes. Heisenberg's original 1927 paper introduced the uncertainty principle through thought experiments involving microscopes and photons. He imagined trying to measure an electron's position by bouncing a photon off it. To localize the electron precisely, you need a short wavelength photon, but short wavelengths mean high momentum. So the photon kicks the electron hard, disturbing its momentum. These arguments are pedagogically useful, but somewhat misleading because they suggest the uncertainty is about measurement disturbance. The deeper understanding came from the mathematical structure of quantum mechanics itself. Max Born and Pascual Jordan had developed the formalism showing that position and momentum were represented by non-commuting operators. Any pair of non-commuting observables has an associated uncertainty relation. The uncertainty isn't a feature of measurement. It's a feature of how these properties are related in quantum theory. Erwin Schrödinger, working simultaneously but independently, developed wave mechanics, where particles were described by wave functions. In this picture, the uncertainty principle emerges from the mathematics of waves. A wave packet, a localized disturbance that represents a particle, cannot be perfectly localized in both position and wavelength. If you make it localized in position, it must contain many different wavelengths. If you make it a pure wavelength, it spreads out infinitely in space. Since wavelength is inversely related to momentum, this is just another way of stating the uncertainty principle. The two formulations, Heisenberg's matrices and Schrödinger's waves, were proven mathematically equivalent by Jan von Neumann and others. They're different mathematical languages describing the same physics. Heisenberg's version emphasizes observables and measurements. Schrödinger's version emphasizes waves and evolution. Both lead to the same uncertainty principle, suggesting it's not an artifact of one particular approach, but something fundamental to quantum behavior. Heisenberg and Bohr engaged in intense discussions about the interpretation of uncertainty. Bohr introduced the concept of complementarity, the idea that certain pairs of properties, like position and momentum, or wave and particle nature, are complementary. You can measure one or the other, but attempting to measure both simultaneously is incoherent. The experimental setup that reveals position necessarily obscures momentum, and vice versa. Einstein was deeply troubled by all of this. He engaged Bohr in a series of debates, proposing thought experiments intended to demonstrate that the uncertainty principle could be violated or that quantum mechanics was incomplete. Each time, Bohr found flaws in Einstein's arguments, often using Einstein's own theories of relativity to show that the uncertainty principle held up. One famous exchange involved Einstein proposing a box with a shutter containing photons. Open the shutter briefly to let a photon escape. Weigh the box before and after to determine the photon's energy from E mc2 and time the shutter opening precisely. This would seem to violate the time-energy uncertainty principle. Bohr, after a sleepless night, realized that the act of weighing the box in a gravitational field introduced a time uncertainty through gravitational time dilation, exactly enough to preserve the uncertainty principle. These debates clarified the principle, but didn't resolve the deeper conceptual issues. The uncertainty principle is mathematically clear and experimentally verified countless times. But what it means about the nature of reality remains contested. Does it mean particles don't have definite properties until measured? Does it mean we're just ignorant of hidden variables that would restore definiteness? Does it mean something even stranger? These questions will lead us into the full machinery of quantum mechanics, the wave function, the Schrödinger equation, and eventually the measurement problem. But for now, understand this. Uncertainty is not a bug in quantum mechanics. It's a central feature. It's what keeps atoms stable, what gives particles their zero-point energy, what makes the quantum world fundamentally different from the classical world we experience. And it all follows from one simple fact. Position and momentum don't commute. The wave function. By 1926, quantum mechanics was a collection of successful but disconnected ideas. Planck's quanta explained black body radiation. Einstein's photons explained the photoelectric effect. Bohr's quantized orbits explained atomic spectra. De Broglie's matter waves explained why those orbits were quantized. But there was no unified framework, no single equation that could predict quantum behavior from first principles. Two physicists, working independently and with very different approaches, developed complete theories within months of each other. Werner Heisenberg, working with Max Born and Pascual Jordan, created matrix mechanics, where physical quantities were represented by arrays of numbers that obeyed specific algebraic rules. Erwin Schrödinger developed wave mechanics, where particles were described by wave functions that evolved according to a differential equation. The approaches seemed entirely different, philosophically and mathematically. Heisenberg's matrices emphasized discrete quantities and sudden quantum jumps. Schrödinger's waves emphasized continuity and smooth evolution. The two men disliked each other's formulations. Heisenberg found Schrödinger's waves too classical, too comfortable. Schrödinger found Heisenberg's matrices abstract and physically opaque. It didn't matter. Within a year, it was proven that the two formulations were mathematically equivalent. different representations of the same underlying theory. You could translate any problem from one language to the other and get the same physical predictions. Today, most physicists learn Schrödinger's wave mechanics first because the mathematics is more familiar, but both approaches survive in different contexts. Schrödinger's wave function is usually denoted by the Greek letter psi. See? For a single particle in one dimension, it's a function of position and time. Pos, haus, ak, haus, t. This means at each point in space and at each moment in time, the wave function has a value. That value is generally a complex number, involving both real and imaginary parts, which is one of the first hints that we're not dealing with ordinary physical waves like sound or water. What does the wave function represent? Schrödinger himself initially thought peace represented a physical wave, perhaps a smeared-out electron spread through space. This interpretation failed almost immediately. For one thing, if you have two electrons, the wave function depends on both their positions, pas, since 2t. That's not a wave in ordinary three-dimensional space. It's a wave in a six-dimensional configuration space. Add more particles, and the dimensions multiply. For a system of n particles, the wave function lives in a 3n dimensional space. This is not just mathematically abstract. It has physical consequences. The wave function for two electrons can't be separated into two independent wave functions, one for each electron. The electrons are described by a single wave function that depends on both positions simultaneously. This is entanglement, and we'll return to it later, but for now, note that the wave function is not a wave in physical space. It's something stranger. The correct interpretation came from Max Born in 1926. Born proposed that the wave function itself wasn't directly observable. What mattered was its squared magnitude. 2. At any position, x, the quantity, Socrates x or t, 2, gives the probability density of finding the particle at that location if you measure its position at time t. This is a radical departure from classical physics. In classical mechanics, a particle has a definite position and momentum at all times, whether you measure them or not. In quantum mechanics, before measurement, the particle doesn't have a definite position. It has a wave function that encodes probabilities for where it might be found. The particle is, in some sense, spread out according to Poisson's 2, until a measurement localizes it. The wave function must satisfy certain requirements. It must be normalized, meaning if you integrate Poisson 2 over all space, you get one. This ensures that the total probability of finding the particle somewhere is 100%. If the wave function isn't normalized, you can multiply it by a constant to fix that, so the overall scale doesn't matter. What matters is the relative probabilities at different locations. The wave function can also have a phase, a complex number factor that doesn't affect its 2, but does affect how different parts of the wave function interfere with each other. This phase is crucial for understanding interference patterns and quantum superposition. Two wave functions that differ only by a phase factor represent the same physical state in terms of measurement probabilities. But they can interfere differently. Here's where superposition enters. If but is a possible wave function, and psi 2 is another possible wave function, then any combination a plus 1 plus b plus 2 is also a valid wave function, where a and b are complex numbers. This is the principle of superposition, and it's one of the defining features of quantum mechanics. Superposition means that if a particle can be in state 1 or state 2, it can also be in a state that's a combination of both. Not sometimes one and sometimes the other, but genuinely both simultaneously. Before measurement, the particle exists in this superposition state. Measurement forces it to become one or the other. This is not a statement about our knowledge. It's not that the particle is really in state 1 or state 2, and we just don't know which. The particle is in the superposition state, and that superposition has physical consequences. Different superpositions, even if they're combinations of the same basic states, can produce different interference patterns, different measurement statistics, different physical behavior. The canonical example is Schrödinger's cat, proposed by Schrödinger himself in 1935 as a thought experiment to highlight what he saw as the absurdity of the Copenhagen interpretation. Place a cat in a sealed box with a device that has a 50% chance of releasing poison in 1 hour. After an hour, before you open the box, the quantum state of the device is a superposition of poison released and poison not released. If the cat's state is entangled with the device, the cat should be in a superposition of dead and alive. Schrödinger intended this as a reductio ad absurdum, proof that something was wrong with quantum mechanics or its interpretation. Surely cats aren't in superpositions of alive and dead. Surely macroscopic objects have definite states. But quantum mechanics, taken seriously, seems to say the cat is in superposition until you open the box and measure. This is the measurement problem, and it remains unsolved. We'll discuss various interpretations later, but for now, understand that the wave function's collapse upon measurement, its sudden transition from superposition to a definite state, is not described by the Schrödinger equation. The equation describes smooth, deterministic evolution. Measurement involves something else, something discontinuous and probabilistic. The Schrödinger equation itself, in its time-dependent form, looks like this conceptually. The rate of change of the wave function with respect to time equals a specific operator acting on the wave function, multiplied by I and divided by h bar. The operator, called the Hamiltonian, represents the total energy of the system. For a single particle, the Hamiltonian includes kinetic energy, which depends on momentum, and potential energy, which depends on position. The momentum operator in the wave function picture involves taking derivatives of the wave function with respect to position. This connection between momentum and spatial derivatives is what makes the uncertainty principle emerge naturally from wave mechanics. Solving the Schrödinger equation means finding wave functions that satisfy the equation given specific physical conditions. For time-independent problems, where the potential energy doesn't change with time, you can separate the time dependence and solve a simpler equation for the spatial part of the wave function. These solutions are called energy eigenstates, states with definite energy. The particle in a box is the simplest non-trivial example. Imagine an infinitely deep potential well, a region where the particle can move freely but cannot escape. Outside the box, the potential energy is infinite, so the wave function must be zero there. Inside the box, the potential energy is zero, so the particle has only kinetic energy. The boundary conditions that the wave function must go to zero at the walls quantize the allowed solutions. Only certain wavelengths fit inside the box, specifically those where an integer number of half wavelengths equals the Box length. This gives discrete energy levels, with energy proportional to n2, where n is a positive integer. The ground state, n(1), has the lowest energy, set by the uncertainty principle. Higher states have more nodes, points where the wave function crosses zero, and correspondingly higher energies. The quantum harmonic oscillator is another foundational problem. A particle in a parabolic potential well, like a mass on a spring, has equally spaced energy levels. The spacing is h times the classical oscillation frequency. The ground state energy is not zero, but rather h times frequency divided by 2. Again, a consequence of zero-point energy. The wave function for the ground state is a Gaussian, a bell curve centered at the equilibrium position. Higher energy states have more elaborate wave functions with more nodes, and these wave functions extend farther from the center. As you go to very high quantum numbers, the probability distribution starts to resemble what classical physics would predict, though the individual wave functions still show quantum oscillations. This is an example of the correspondence principle, that quantum mechanics approaches classical mechanics in appropriate limits. The hydrogen atom, a single electron orbiting a proton, is solved in 3 dimensions with a potential energy that falls off as 1 over the distance from the nucleus. The solutions are characterized by 3 quantum numbers: n, the principal quantum number that determines energy; L, the orbital angular momentum quantum number; and m, which specifies the angular momentum's projection along a chosen axis. These quantum numbers aren't arbitrary labels. They emerge from the mathematics of solving the Schrödinger equation in spherical coordinates. The principal quantum number n must be a positive integer. For each n, L can range from 0 to n1. For each L, m can range from negative L to positive L. These restrictions come from requiring the wave function to be well-behaved, single-valued, and normalizable. The resulting wave functions, called atomic orbitals, have distinctive shapes. The L0 states are spherically symmetric. The L1 states have dumbbell shapes pointing along different axes. Higher angular momentum states have more complex geometries with multiple lobes and nodal surfaces. These shapes aren't just mathematical curiosities. They determine chemical bonding, how atoms interact to form molecules, the entire field of chemistry. Each orbital can hold 2 electrons with opposite spins, a consequence of the Pauli exclusion principle, which says no 2 fermions can occupy the same quantum state. This builds up the periodic table. Hydrogen has 1 electron in the n1, L0 state. Helium has 2 electrons filling that state. Lithium starts filling n2. Chemical properties of elements are determined by their electron configurations, which are governed by the solutions to the Schrödinger equation. For systems more complex than hydrogen, the Schrödinger equation can't be solved exactly. The mutual repulsion between electrons makes the mathematics intractable. Physicists use approximation methods, perturbation theory for small effects, variational methods to estimate ground states, and numerical computation for detailed predictions. Modern quantum chemistry consists largely of developing better approximations and more efficient numerical algorithms. But in all cases, the wave function remains central. It encodes everything quantum mechanics can tell you about a system. From the wave function, you can calculate probabilities for any measurement. position, momentum, energy, angular momentum. Any observable quantity has an associated operator, and the wave function determines the statistics of measurements for that quantity. The wave function evolves deterministically according to the Schrödinger equation. Given the wave function at one time, you can calculate it at any future or past time with certainty. There's no randomness in the evolution itself. The randomness, the probability, enters when you make a measurement. This is the measurement problem in its starkest form. The Schrödinger equation is deterministic and continuous. Measurement outcomes are probabilistic and discrete. Something happens during measurement that's not described by the Schrödinger equation, something that collapses the wave function from a superposition into a definite state. What causes this collapse? When does it happen? Does it actually happen? Or is collapse an illusion arising from our limited perspective? These questions have no agreed-upon answers. The Copenhagen interpretation, developed by Bohr and Heisenberg, says measurement causes collapse, but doesn't specify what counts as measurement. The many worlds interpretation, proposed by Hugh Everett, says there's no collapse, just branching of the universal wave function into separate worlds. Pilot wave theory, or de Broglie-Bohm theory, says particles always have definite positions guided by the wave function, avoiding collapse entirely, but at the cost of non-locality. We'll explore these interpretations in detail later. For now, understand that the wave function formalism works spectacularly well for calculations and predictions. Quantum mechanics is the most precisely tested theory in physics, with some predictions verified to 10 decimal places or more. But what the wave function represents, what it tells us about the nature of reality, remains genuinely unclear nearly a century after Schrödinger wrote down his equation. The Schrödinger equation and solutions. The Schrödinger equation is to quantum mechanics what Newton's second law is to classical mechanics, the fundamental equation of motion. But where Newton's law tells you how particles accelerate in response to forces, Schrödinger's equation tells you how wave functions evolve in response to potentials. The difference is profound. There are actually two forms of the Schrödinger equation, time-dependent and time-independent. The time-dependent version describes how wave functions change as time passes. The time-independent version applies to systems where the potential energy doesn't change with time, and it's used to find energy eigenstates, states with definite energy that form the building blocks for more general solutions. For a single particle in one dimension, the time-independent Schrödinger equation can be written conceptually as follows. An energy term times the wave function equals an operator acting on the wave function. The operator includes two pieces. First, a term involving the second spatial derivative of the wave function, which represents kinetic energy. Second, a term involving the potential energy at each position, which represents the forces acting on the particle. The second derivative term captures the wave nature of quantum mechanics. Classical kinetic energy depends on velocity squared, or equivalently momentum squared. In wave mechanics, momentum is related to wavelength, and wavelength is encoded in how rapidly the wave function oscillates in space. High curvature means short wavelength means high momentum means high kinetic energy. The second derivative measures exactly this curvature. The potential energy term V high describes the environment. For a free particle, V is 0 everywhere. For a particle in a box, V is 0 inside the box and infinite at the walls. For a harmonic oscillator, V increases quadratically with distance from equilibrium. For hydrogen, V is the Coulomb attraction between electron and proton, falling off as -1 over the distance. Solving the equation means finding functions Poisson-Checks that satisfy this relationship for a given potential Vx and a given energy E. These solutions are the allowed quantum states. Not every mathematical function works. The wave function must be continuous, must be normalizable, and must have a continuous derivative except at points where the potential is infinite. These requirements quantize the allowed energies. Let's examine 3 archetypal problems where the Schrödinger equation can be solved exactly. These aren't just textbook exercises. They're templates that illuminate how quantization emerges and why quantum systems behave the way they do. The infinite square well, or particle, in a box is the simplest. A particle is confined to a region of width L between x0 and x0. Inside this region, the potential energy is 0. Outside, it's infinite, meaning the particle absolutely cannot exist there. The wave function must therefore vanish at x0 and xESL. Inside the box, with V0, the Schrödinger equation reduces to a statement about the second derivative of Pes. The solutions are sine waves, oscillating functions. But the boundary conditions restrict which sine waves are allowed. The wavelength must fit evenly into the box. Specifically, you need an integer number of half wavelengths to span the distance L. This immediately quantizes the energy. The allowed wavelengths are 2Ln, where n is a positive integer. Using de Broglie's relation connecting wavelength to momentum and the classical relation connecting momentum to kinetic energy, you find that energy is proportional to n2. The quantum number n labels the state. N number 1 is the ground state with lowest energy. N number 2 is the first excited state with 4 times the ground state energy. N number 3 has 9 times the ground state energy, and so on. The ground state wave function is a single, smooth hump, a half wavelength of a sine wave spanning the box. It has no nodes, no points where it crosses 0 inside the box. The first excited state has 1 node in the middle, forming 2 humps. Higher states have more nodes. Each node represents a sign change in the wave function. And these sign changes are crucial for interference effects. The ground state energy is not 0. Even in the lowest possible energy state, the particle has kinetic energy equal to P2 times 2 divided by 2mL2, where m is the particle mass. This is zero-point energy arising from the uncertainty principle. Confining the particle to width L means its position uncertainty is about L, which requires momentum uncertainty of at least at L, which translates to kinetic energy. As the box gets smaller, the ground state energy increases. Squeeze the particle tighter and it wiggles faster. This is why atomic nuclei, which confine protons and neutrons to regions about 10 to 15 meters across, involve such high energies. The confinement itself generates enormous kinetic energies, which is why nuclear reactions release so much energy, and why quantum tunneling out of nuclei, radioactive decay, is possible despite the strong attractive forces. The quantum harmonic oscillator describes a particle in a parabolic potential well, like a mass attached to a spring. Classically, such a system oscillates with a frequency determined by the spring constant and mass. Quantum mechanically, the energy levels are equally spaced, separated by times the classical frequency. The ground state energy is O toward 2, where O is the angular frequency, not 0. Again, 0-point energy prevents the particle from simply sitting at the bottom of the well. The wave function for the ground state is a Gaussian, a bell curve centered at equilibrium. This shape minimizes the sum of kinetic and potential energy while respecting the uncertainty principle. Higher energy states have more elaborate wave functions. The first excited state has one node, the second has two nodes, and so forth. These wave functions are products of Gaussians and Hermite polynomials, mathematical functions that form a complete orthogonal set. Any wave function for a harmonic oscillator can be written as a superposition of these energy eigenstates. The harmonic oscillator is more than an academic exercise. Molecular vibrations are approximately harmonic. Electromagnetic fields can be decomposed into harmonic oscillator modes, which is the starting point for quantum field theory and the quantum description of photons. Phonons, quantized vibrations in solids, are harmonic oscillators. Understanding this system is essential for condensed matter physics, quantum optics, and particle physics. One peculiar feature is that the probability distribution extends beyond the classical turning points, the positions where a classical particle would stop and reverse direction. A quantum particle has some probability of being found where it classically shouldn't be. This is tunneling into the classically forbidden region, though for the harmonic oscillator, the particle can't actually escape because the potential rises indefinitely. The hydrogen atom is the crown jewel of exactly solvable quantum systems. A single electron orbiting a proton under Coulomb attraction gives a three-dimensional problem requiring spherical coordinates. The potential energy is negative, E2R, where E is the elementary charge and ER is the distance from the nucleus. Solving the Schrödinger equation in 3 dimensions with this potential yields wave functions characterized by 3 quantum numbers. The principal quantum number n determines the energy. The orbital angular momentum quantum number L determines the magnitude of angular momentum. The magnetic quantum number m determines the angular momentum component along a chosen axis. The energy depends only on n, not on L or m. The formula is E Schars 13.6 eV divided by n2, exactly matching what Bohr had postulated. But Schrödinger's wave mechanics derived this from first principles. Quantization wasn't imposed. It emerged from requiring the wave function to be normalizable and well-behaved everywhere. For each value of n, L can range from 0 to n mod 1. For each IL, m ranges from UdL to plus L. This gives multiple states with the same energy, called degeneracy. For example, N-2 includes 4 states, 1 with L and 3 with L and M1, 0, 0, or plus 1. All 4 have the same energy, 3.4 eV, though they have different wave functions with different spatial distributions. The L0 states are called s orbitals and are spherically symmetric. The L1 states are p orbitals with dumbbell shapes pointing along different axes. The L2 states are d orbitals with more complex 4-lobed patterns. These shapes aren't arbitrary. They're solutions to the angular part of the Schrödinger equation, called spherical harmonics, and they determine how atoms bond to form molecules. The radial part of the wave function depends on both n and L. For the ground state, n was 1, L was 0, the wave function decays exponentially with distance from the nucleus. The probability density peaks at the Bohr radius, about 0.53 angstroms, but extends to infinity, never quite reaching zero. There's always some small probability of finding the electron far from the nucleus. Higher states have more complex radial structure with nodes where the radial wave function passes through zero. These nodes create shells of high and low probability. The N-2 L0 state has one radial node, creating an inner region and an outer region of high probability, separated by a spherical surface where the probability is zero. Spin, the intrinsic angular momentum of the electron, adds another quantum number, typically denoted S with values +1, 2. Spin isn't described by the basic Schrödinger equation. It emerged from Dirac's relativistic quantum mechanics, but can be incorporated into non-relativistic quantum mechanics as an additional degree of freedom. Each spatial orbital can hold two electrons with opposite spins, the basis of the Pauli exclusion principle. Building up the periodic table involves filling these orbitals with electrons while respecting the exclusion principle. Hydrogen has one electron in the N-1, L0 state. Helium has two electrons filling that state with opposite spins. Lithium starts filling N-2. The electron configuration determines chemical behavior. Noble gases have filled shells and are inert. Alkali metals have one electron beyond a filled shell and are highly reactive. The Schrödinger equation for multi-electron atoms can't be solved exactly because electrons repel each other. The potential energy includes not just electron-nucleus attraction, but also electron-electron repulsion, and the latter makes the problem intractable. Approximate methods are required. The simplest approximation treats each electron as moving in an average potential created by the nucleus and all other electrons. This is the mean field, or Hartree-Fock approximation. It's not exact, but captures the essential physics and explains the periodic table's structure reasonably well. More sophisticated methods include configuration interaction, where you consider superpositions of different electron configurations, and density functional theory, where the focus shifts from wave functions to electron density. Modern computational chemistry uses these methods to predict molecular structures, reaction rates, and material properties with impressive accuracy. But all of these rest on the foundation of the Schrödinger equation and its solutions for hydrogen. The quantum numbers AN, L, M that emerge from solving for one electron in a Coulomb potential organize all of chemistry. The energies, spacings, and selection rules for atomic transitions govern spectroscopy and determine which frequencies of light atoms absorb and emit. These exactly solvable systems, the infinite square well, harmonic oscillator, and hydrogen atom, are more than teaching tools. They're building blocks. Many realistic potentials can be approximated by these forms over limited regions. A particle trapped in a potential well approximates a square well. A particle near the bottom of any smooth potential well sees approximately a harmonic oscillator potential. Multiple particles interacting through Coulomb forces can sometimes be reduced to hydrogen-like problems. And the techniques developed for these systems, separation of variables, boundary conditions, orthogonal function expansions, perturbation theory, all extend to more complex situations. The infinite square well teaches you how boundary conditions quantize energy. The harmonic oscillator teaches you about ladder operators and Fock space, essential for quantum field theory. The hydrogen atom teaches you about angular momentum and how symmetries generate degeneracies and selection rules. In each case, quantization emerged not from ad hoc postulates, but from mathematical requirements on the wave function. Energy couldn't be continuous because continuous energy solutions didn't satisfy the boundary conditions or weren't normalizable. The allowed states formed discrete sets labeled by integers, and those integers became the quantum numbers that organize atomic physics. This is the power of the Schrödinger equation. Given a potential, you can in principle calculate everything quantum mechanics predicts about the system. The challenge is that most potentials don't yield to exact solution. You need approximations, numerical methods, or clever mathematical tricks. But the framework is clear, and the predictions, when compared to experiment, are spectacularly accurate. Quantum tunneling. There's a phenomenon in quantum mechanics that has no classical analog whatsoever. No approximation or limiting case where classical physics predicts anything similar. It's called quantum tunneling, and it's responsible for nuclear fusion in the Sun, the decay of radioactive atoms, the operation of scanning tunneling microscopes, and certain types of chemical reactions in your body right now. In classical physics, if a particle doesn't have enough energy to overcome a barrier, it doesn't get through. A ball rolled toward a hill will climb partway up, slow down, stop, and roll back. It will never appear on the other side unless it had enough kinetic energy to reach the top. This is absolute. Energy is conserved, and barriers are impenetrable to particles lacking sufficient energy. Quantum mechanics says otherwise. A particle encountering a barrier has some probability of appearing on the other side even if its energy is less than the barrier height. It doesn't go over the barrier. It goes through it, emerging with the same energy it started with, as if the barrier momentarily didn't exist. This isn't a small correction to classical behavior. It's a fundamentally different phenomenon, and it's not rare or exotic. Tunneling occurs constantly in systems ranging from atomic to macroscopic scales, anywhere quantum effects remain significant. To understand tunneling, we need to examine what happens to a wave function when it encounters a potential barrier. Imagine a rectangular barrier, a region where the potential energy suddenly jumps to some value V0 and extends for a width L before dropping back to zero. A particle with energy E less than V0 approaches from the left. Classically, the particle should reflect off the barrier like a ball bouncing off a wall. Quantum mechanically, the wave function behaves differently. In the region before the barrier, the wave function oscillates, representing a particle with definite momentum moving toward the barrier. At the barrier, something peculiar happens. Inside the barrier, in the classically forbidden region, the wave function doesn't oscillate. It decays exponentially. The wave function doesn't become zero immediately at the barrier edge. It penetrates into the barrier, diminishing as it goes deeper. The rate of decay depends on the barrier height and the particle mass. Higher barriers and heavier particles lead to faster decay. If the barrier is thin enough, the wave function hasn't completely decayed by the time it reaches the far side. On the far side, the wave function resumes oscillating, representing a particle continuing with the same energy and momentum it had before the barrier. The wave function connects smoothly across all regions. There's an incoming wave, a decaying portion inside the barrier, and a transmitted wave on the far side. The probability of transmission depends on the height and width of the barrier and on the particle's energy and mass. For thick, high barriers and heavy particles, transmission probability is negligible. For thin, low barriers and light particles, it can be substantial. The exponential decay inside the barrier means transmission probability drops off very rapidly as barriers get thicker or higher. The mathematics involves matching the wave function and its derivative at the barrier boundaries. This ensures the wave function is continuous and smooth. The result is a transmission coefficient, a number between 0 and 1, giving the fraction of particles that tunnel through. Even when this number is tiny, say 1030, it can have observable consequences if you have enough particles or enough time. Radioactive decay is perhaps the most dramatic example of tunneling. Alpha decay occurs when an atomic nucleus ejects an alpha particle, a cluster of 2 protons and 2 neutrons. Inside large nuclei, alpha particles are bound by the strong nuclear force, trapped in a potential well. But they're trying to escape, pushed out by electromagnetic repulsion between the positively charged alpha particle and the remaining positively charged nucleus. The potential energy looks like a well inside the nucleus with high walls surrounding it. An alpha particle inside the nucleus doesn't have enough energy to classically escape over the barrier. The Coulomb repulsion would require much more energy than the alpha particle possesses. Yet alpha particles do escape. Uranium-238 decays by alpha emission with a half-life of 4.5 billion years. The alpha particle is tunneling through the barrier. George Gamow explained alpha decay using quantum tunneling in 1928, just 2 years after the Schrödinger equation was published. He calculated the tunneling probability and showed it matched the observed decay rates. Different isotopes have different barrier shapes and different tunneling probabilities, explaining why half-lives vary from microseconds to billions of years. The Sun provides another example. Nuclear fusion in the Sun's core combines hydrogen nuclei to form helium, releasing energy that ultimately powers all life on Earth. But there's a problem. Hydrogen nuclei are positively charged protons. They repel each other electromagnetically. To fuse, they must get close enough for the strong nuclear force to bind them, within about 10 to 15 meters. The electromagnetic repulsion creates a potential barrier. Classically, protons would need temperatures of about 1010 Kelvin to have enough kinetic energy to overcome this barrier. The Sun's core is hot, around 15 million Kelvin, but nowhere near hot enough for classical fusion. Quantum tunneling solves this. Protons don't need enough energy to go over the barrier. They can tunnel through it. The tunneling probability is small for any individual collision, but the Sun's core contains enormous numbers of protons colliding constantly. Even a tiny tunneling probability per collision adds up to sufficient fusion rate to power the Sun. Without quantum tunneling, stars wouldn't shine and life wouldn't exist. The scanning tunneling microscope, invented in 1981 by Gerd Bienig and Heinrich Rohrer, who won the Nobel Prize for it in 1986, uses quantum tunneling to image individual atoms. A sharp metal tip is brought very close to a conducting surface, within a nanometer or so. At this distance, the wave functions of electrons in the tip overlap with wave functions of electrons in the surface. A voltage applied between tip and surface creates a potential difference. but there's a gap, a vacuum barrier between them. Classically, electrons shouldn't be able to cross this gap. Quantum mechanically, they can tunnel through it. A tiny current flows, called the tunneling current, which depends exponentially on the gap width. As the tip scans across the surface, the tunneling current varies. Where the surface is higher, the gap is narrower and the current is larger. Where the surface is lower, the gap is wider and the current is smaller. By monitoring the current and adjusting the tip height to keep the current constant, you can map the surface topography with atomic resolution. Every bump and valley represents individual atoms. The exponential sensitivity to distance is remarkable. Moving the tip closer by just 1 angstrom, 1/10 of a nanometer, can increase the tunneling current by a factor of 10. This makes the scanning tunneling microscope one of the most precise measuring instruments ever created. It can detect height variations of 1/100th of an angstrom, a small fraction of an atomic diameter. Quantum tunneling also occurs in chemical reactions. Many reactions involve rearranging atoms, breaking old bonds and forming new ones. Sometimes a hydrogen atom, or more precisely a proton, must move from one molecule to another. Classically, this requires climbing over an energy barrier, the activation energy. With sufficient thermal energy, reactions proceed at rates determined by temperature and barrier height. But at low temperatures, classical reactions should freeze out. Molecules don't have enough thermal energy to overcome barriers. Yet some reactions continue at rates faster than classical predictions. Protons are light, so their de Broglie wavelength is relatively large, and they can tunnel through barriers that would classically stop them. Enzyme catalysis in biology often involves proton tunneling. Enzymes lower activation energy barriers, but even the lowered barriers might be too high for classical reactions at body temperature. Tunneling contributes to the speed of enzymatic reactions, allowing life's chemistry to proceed rapidly enough to sustain metabolism. There's even evidence that tunneling plays a role in mutations. DNA mutations sometimes occur when a hydrogen atom in a base pair tunnels from one configuration to another, creating a tautomeric form that mispairs during replication. This is speculative, but quantum tunneling might contribute to the spontaneous mutation rate that drives evolution. The ammonia molecule provides a beautiful example of tunneling in molecular systems. Ammonia, NH3, is pyramid-shaped with the nitrogen atom at the apex and 3 hydrogen atoms forming the base. The nitrogen can be above or below the plane of hydrogens. These are 2 equivalent configurations separated by a potential barrier. Classically, if you put the nitrogen above the plane, it should stay there. The barrier prevents it from moving to the below configuration without enough energy to flip the molecule over. Quantum mechanically, the nitrogen can tunnel through the barrier, oscillating between the 2 configurations. This tunneling creates a splitting of energy levels. What would classically be a single state becomes 2 states with slightly different energies. The frequency corresponding to this energy difference is about 24 gigahertz in the microwave range. This is the inversion frequency of ammonia, and it's been measured with extraordinary precision. Ammonia masers, microwave lasers, exploit this transition. Tunneling also explains why hydrogen bonds, important in water and DNA, have the properties they do. A hydrogen atom shared between two oxygen or nitrogen atoms can tunnel between them, creating a delocalized bond with characteristics intermediate between covalent and ionic bonding. The details of hydrogen bonding, crucial for protein folding and DNA structure, involve quantum tunneling of protons. There are limits to tunneling. As systems get larger and barriers get thicker, tunneling probability drops exponentially. For macroscopic objects, tunneling is effectively impossible. You cannot tunnel through a wall by walking into it, not because the probability is small, but because it's unmeasurably, inconceivably tiny. The exponential dependence on barrier width and particle mass makes tunneling a quintessentially quantum phenomenon that disappears at large scales. This is part of why we don't see quantum effects in everyday life. Not just because h-bar is small, but because probabilities become exponentially suppressed for massive objects and thick barriers. Still, quantum tunneling is ubiquitous at atomic scales. Electrons and molecules tunnel between atoms. Protons tunnel through barriers in chemical reactions. Alpha particles tunnel out of nuclei. Cooper pairs, bound electron pairs in superconductors, tunnel through insulating barriers in Josephson junctions. Devices used in superconducting quantum computers and sensitive magnetometers. Tunneling is also central to many modern technologies. Flash memory in USB drives and solid-state hard drives stores data by trapping electrons in isolated regions. Writing and erasing data involves using high voltages to make electrons tunnel into and out of these regions. Tunnel diodes, where electrons tunnel through thin barriers, exhibit negative resistance and are used in high-frequency oscillators. The conceptual challenge of tunneling is understanding what's actually happening. The particle doesn't have a continuous trajectory through the barrier. You can't track it moving from one side to the other. If you try to measure its position inside the barrier, you'll either find it or not, and if you find it, you've disrupted the tunneling process. The wave function extends into the barrier and beyond. The particle has some amplitude to be on the far side. When you measure position, the wave function collapses, and you might find the particle has appeared on the far side. It didn't travel through the barrier in any classical sense. It simply had non-zero amplitude to be there, and measurement actualized one possibility. This is why tunneling doesn't violate energy conservation. The particle on the far side has the same energy it started with. It didn't borrow energy to climb the barrier. It never climbed. Tunneling is not a particle going somewhere it classically couldn't go. It's the wave function having amplitude in classically forbidden regions, and measurement outcomes reflecting that amplitude. Quantum tunneling is one of the clearest demonstrations that quantum mechanics is not just a modification of classical mechanics, not just adding some uncertainty or discreteness to otherwise classical behavior. It's a fundamentally different description of nature where particles are described by wave functions that obey the Schrödinger equation. And those wave functions extend into and through barriers that would absolutely, definitively stop classical particles. Without tunneling, the universe would be a very different place. Quantum entanglement. In 1935, Albert Einstein was deeply unhappy with quantum mechanics. He'd helped to create it with his work on the photoelectric effect, but the probabilistic interpretation troubled him profoundly. Einstein believed in an objective reality, a universe that existed independent of observation, where particles had definite properties, whether you measured them or not. Together with two colleagues, Boris Podolsky and Nathan Rosen, Einstein published a paper titled "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" It's now known as the EPR paper, after the author's initials. The paper presented a thought experiment designed to show that quantum mechanics must be incomplete, that something was missing from the theory. The argument goes like this. Consider two particles that interact and then separate, flying off in opposite directions. Quantum mechanics describes them with a single entangled wave function, not as two independent particles, but as a correlated system. You can measure properties of one particle, say its position, and immediately know something about the other particle, even if it's now across the room or across the galaxy. Einstein found this absurd. How could measuring one particle instantaneously affect the other? Information can't travel faster than light according to relativity, which Einstein himself had established. Yet quantum mechanics seem to require that particles remain connected regardless of distance, influencing each other instantaneously. Einstein proposed two alternatives. Either the influence really does travel faster than light, violating relativity, or the particles had definite properties all along. Properties determined when they separated, and measurement simply reveals pre-existing values rather than creating them. Quantum mechanics must be incomplete, Einstein argued, missing some deeper variables that would restore definite properties and eliminate the spooky action at a distance. Niels Bohr disagreed. He argued that the two particles remain part of a single quantum system until measurement. You can't talk about the properties of one particle independently of the other. They're entangled, and that entanglement is a fundamental feature of quantum mechanics, not a defect needing repair. For 3 decades, this remained a philosophical debate. Both sides had consistent arguments, but no one could devise an experiment to settle the question. Entanglement seemed like one of those interpretation issues that wouldn't affect actual predictions. Then, in 1964, a physicist named John Stuart Bell changed everything. Bell was working at CERN, the European Particle Physics Laboratory, thinking about the EPR paradox during his spare time. He asked a precise question. If particles had hidden variables, predetermined properties that quantum mechanics didn't describe, what correlations would you observe in measurements? Bell derived an inequality, a mathematical relationship that any theory based on local hidden variables must satisfy. Local means influences can't travel faster than light. Hidden variables means particles have definite properties before measurement. If nature obeys local realism, measurement correlations must stay within certain bounds, limits set by Bell's inequality. Quantum mechanics predicts violations of Bell's inequality. For certain configurations of measurements on entangled particles, quantum mechanics predicts stronger correlations than any local hidden variable theory could produce. This was remarkable. Bell had found a way to experimentally test whether Einstein or Bohr was right, whether quantum mechanics was complete or missing something. The experiments took time to develop. You need to create entangled particles, separate them, measure correlated properties, and repeat many times to build up statistics. The first tests in the 1970s by John Clauser and Stuart Friedman supported quantum mechanics. Experiments by Alain Aspect in the early 1980s were more sophisticated, closing certain loopholes, and again confirmed quantum predictions. Modern experiments are extraordinarily precise. In 2015, experiments closed the remaining significant loopholes simultaneously. The results are unambiguous. Nature violates Bell's inequalities. Quantum mechanics is correct, and local hidden variable theories are ruled out. This means one of two things, and possibly both, must be true. Either nature is not local, meaning measurements at one location can instantaneously affect outcomes at distant locations, or nature is not real in Einstein's sense, meaning particles don't have definite properties before measurement. Most physicists accept non-locality. Entangled particles remain correlated regardless of distance in a way that can't be explained by local interactions or pre-existing properties. Let's make this concrete. Consider two electrons prepared in an entangled state where their spins are correlated. Electron spin is a quantum property that, when measured along any axis, gives either spin up or spin down. Before measurement, neither electron has a definite spin direction. They're in a superposition, but they're not in independent superpositions. They're entangled. If you measure the first electron's spin along some axis and find spin up, measuring the second electron's spin along that same axis will definitely give spin down. The spins are perfectly anti-correlated. This holds true regardless of which axis you choose to measure along. Before measurement, neither electron has a definite spin. After measuring the first, it has a definite spin. And simultaneously, the second electron's spin becomes definite too, perfectly opposite, even if the electrons are light years apart. The measurement on one particle instantaneously affects the quantum state of the other. This doesn't allow faster-than-light communication. You can't control what result you get when measuring the first electron. It's random. 50% chance of up, 50% chance of down. The person measuring the second electron sees random results too. Only when you compare results do you find the perfect anti-correlation. The comparison requires classical communication, which travels at or below light speed. But the correlation itself, the fact that measurements are linked, is instantaneous and can't be explained by any local mechanism. Bell's theorem proves this mathematically. Any attempt to explain the correlations using local variables, properties the particles carried with them when they separated, predicts weaker correlations than quantum mechanics. Experiments confirm the stronger quantum correlations. This is non-locality. Entangled systems are not separable into independent subsystems. You can't say the first electron is in one state and the second is in another. There's only one state for the pair, and measuring one affects both. Einstein called this spooky action at a distance, and he was right to find it spooky. But experiments show it's how nature actually works. Quantum mechanics is non-local. Space-like separated events, events that can't be connected by light signals, can nevertheless be correlated in ways that seem impossible classically. Entanglement becomes even stranger with more than two particles. You can entangle 3, 4, or more particles into states where measurements on any subset affect the entire group. These multi-particle entangled states, like GHZ states named after Greenberger, Horn, and Zeilinger, show correlations that become increasingly difficult to explain without accepting quantum mechanics wholesale. Entanglement is now routinely created in laboratories. Pairs of photons are entangled by sending a single photon through a special crystal that splits it into two lower energy photons with correlated polarizations. These entangled photons can be separated by kilometers while maintaining their quantum connection. Experiments have demonstrated entanglement over distances exceeding 1 to 200 kilometers using satellite links. The applications are emerging. Quantum cryptography uses entanglement to create provably secure communication channels. Any eavesdropping attempt necessarily disturbs the entangled state, revealing the presence of an eavesdropper. Quantum key distribution systems are already commercially available and used by some government and financial institutions. Quantum computing relies fundamentally on entanglement. A classical computer processes bits that are either 0 or 1. A quantum computer uses qubits that can be in superpositions of 0 and 1. But the real power comes from entangling qubits. With entanglement, the quantum state space grows exponentially with the number of qubits, allowing quantum computers to explore vastly more possibilities simultaneously than classical computers. Quantum teleportation, despite the science fiction associations, is a real phenomenon demonstrated in laboratories. It doesn't teleport matter or energy. It teleports quantum states. If you have an entangled pair of particles, and you want to transfer the quantum state of a third particle to one of the entangled pair, you can do so without the state ever traveling through the intervening space. The process requires both a quantum channel, the entanglement, and a classical channel to send measurement results. The state is destroyed at the original location and recreated at the destination, with perfect fidelity if done correctly. It's been demonstrated with photons, atoms, and recently with superconducting circuits in quantum processors. Entanglement might also play a role in biology, though this is more speculative. Some birds navigate using Earth's magnetic field, and there's evidence they do so via radical pair mechanisms in their eyes involving entangled electrons. Photosynthesis might exploit entanglement to achieve its remarkable efficiency in transferring energy. These claims remain controversial and are actively researched. What makes entanglement philosophically troubling is that it seems to conflict with our intuitive notion of locality, the idea that objects are only directly influenced by their immediate surroundings. Relativity prohibits faster-than-light influences. Yet entanglement creates correlations that seem to require instantaneous connections. The resolution is subtle. Entanglement doesn't allow signaling, so it doesn't violate the prohibition on faster-than-light communication. You can't use entanglement to send messages. The randomness of quantum measurement outcomes prevents that. But entanglement does mean that quantum states are not local. The wave function of an entangled system isn't something you can localize to individual particles. This has led some physicists to suggest that space itself might be emergent from entanglement, that the geometry of space-time could arise from the patterns of quantum entanglement in some more fundamental description of reality. This is highly speculative, but represents serious theoretical work at the intersection of quantum mechanics and general relativity. Different interpretations of quantum mechanics handle entanglement differently. In the Copenhagen interpretation, measurement on one particle collapses the wave function of both, instantaneously creating definite properties. This non-local collapse is simply accepted as how quantum mechanics works. In the many worlds interpretation, measurement doesn't collapse anything. The universe branches, and in each branch, the measurement results are correlated. There's no need for instantaneous action at a distance because there's no collapse. But many worlds has its own strangeness, requiring an ever-multiplying number of parallel realities. In pilot wave theory, particles always have definite positions guided by a wave function that evolves non-locally. Entanglement reflects correlations in the guiding wave. This restores definiteness to particle properties, but at the cost of explicit non-locality in the wave function's dynamics. No interpretation eliminates the weirdness entirely. They redistribute it, trading one kind of strangeness for another. But all must account for the experimental fact that Bell's inequalities are violated, that nature exhibits stronger correlations than local realism allows. Entanglement is now one of the best verified predictions of quantum mechanics. It's not just a theoretical curiosity. It's been demonstrated in countless experiments across different physical systems: photons, electrons, atoms, ions, superconducting circuits. The phenomenon is robust and reproducible, yet it remains deeply counterintuitive. Particles that were once together remain connected regardless of separation. Measuring one affects the other instantaneously. Properties don't exist until measured, but are perfectly correlated when they become definite. Space-like separated events are not independent. This is the quantum world, not the comfortable, intuitive world of everyday experience, but the actual behavior of nature at fundamental scales. Entanglement reveals that the universe is knit together more tightly than classical physics ever imagined, that separateness is less fundamental than we thought, that measurement and reality are intertwined in ways we are still working to understand. The measurement, problem, and interpretations. Quantum mechanics works. This needs to be stated clearly before we dive into the interpretations. The theory makes predictions that have been verified to astonishing precision. The anomalous magnetic moment of the electron, for instance, has been calculated using quantum electrodynamics and measured experimentally, and they agree to 12 decimal places. No other scientific theory comes close to this level of accuracy. But quantum mechanics also has a problem at its core, and that problem has persisted for nearly a century. It's called the measurement problem, and it's this. The Schrödinger equation describes smooth, deterministic evolution of the wave function. Yet measurement produces discrete, probabilistic outcomes. Something happens during measurement that the equation doesn't describe. Before measurement, a particle can be in a superposition of states. An electron's spin can be up and down simultaneously in the quantum sense. Not classically both, but in a superposition where both possibilities have amplitude. The wave function evolves according to the Schrödinger equation, deterministically and continuously. Then you measure. Suddenly, the superposition vanishes. You find the electron either spin up or spin down, never something in between. The wave function collapses from a spread-out superposition to a definite state. This collapse is discontinuous, instantaneous, and random. You can predict the probabilities for different outcomes, but not which specific outcome you'll get. This is strange enough, but it gets worse. What counts as a measurement? When exactly does collapse happen? The Schrödinger equation applies to measuring devices too, since they're made of atoms following quantum laws. If the electron becomes entangled with the measuring device, the combined system should evolve into a superposition of device-measured spin-up and device-measured spin-down. Why does this superposition collapse, but the electrons doesn't? At least not before measurement. You could say collapse happens when a conscious observer looks at the device. But what counts as conscious? Does the observer's brain, also made of quantum particles, go into superposition before the observer becomes conscious of the result? Where in the chain from electron to brain does collapse occur? The measurement problem is not solved. Despite a century of quantum mechanics, despite its spectacular empirical success, we don't have consensus on what happens during measurement, or what the wave function represents. What we have are interpretations, different ways of thinking about quantum mechanics that make identical predictions for experiments, but differ radically in their implications for reality. The Copenhagen interpretation, developed primarily by Niels Bohr and Werner Heisenberg in the 1920s, is historically the first and still the most commonly taught. In Copenhagen, the wave function is not a physical object. It's a mathematical tool for calculating probabilities. Before measurement, particles don't have definite properties. The wave function represents our knowledge, or, more precisely, what can be known about the system. Measurement causes wave function collapse. The act of observation forces the system to take on definite values. Copenhagen doesn't explain what causes collapse or precisely when it happens. It treats measurement as a primitive concept, something fundamental that can't be reduced further. The division between quantum system and classical measuring apparatus is similarly fundamental, a cut that must be made somewhere but whose location is somewhat arbitrary. Bohr introduced complementarity, the idea that certain properties, like position and momentum or wave and particle nature, are complementary. You can measure one or the other, but not both simultaneously. The experimental setup determines which property reveals itself. Reality doesn't have both properties simultaneously waiting to be discovered. The measurement context is inseparable from what's measured. Copenhagen has the virtue of simplicity and direct connection to experimental practice. Physicists calculate using wave functions, perform measurements, and get probabilistic outcomes. Copenhagen describes exactly this process without adding hidden layers, but it leaves the measurement problem unsolved. It doesn't explain collapse, doesn't specify what counts as measurement, and doesn't address why macroscopic objects appear to have definite properties, while quantum objects don't. The many worlds interpretation, proposed by Hugh Everett in 1957 in his Princeton doctoral thesis, takes a radically different approach. In many worlds, there is no wave function collapse. Ever. The Schrödinger equation always applies to everything, with no exceptions. When you measure an electron's spin, the combined system of electron plus measuring device plus you evolves into a superposition. One branch has spin-up electron, device showing up, and you observing up. Another branch has spin-down electron, device showing down, and you observing down. Both branches exist. The universe has split into multiple worlds, and in each world one outcome occurred. You, the observer, also split. One version of you experiences spin-up, another experiences spin-down. Each version is unaware of the other because the branches have decohered, lost their quantum coherence through interactions with the environment. The branches no longer interfere. They are effectively separate worlds. This sounds like science fiction, and Everett's thesis was not well received initially. But many worlds has gained substantial support among physicists and philosophers. It solves the measurement problem by denying that collapse happens. Everything evolves unitarily according to the Schrödinger equation. The appearance of collapse is just you ending up on one branch unable to see the others. Many worlds respects the mathematical structure of quantum mechanics completely. No special treatment of measurement. No arbitrary division between quantum and classical. No mysterious collapse mechanism. The price is ontological extravagance, accepting that every quantum event spawns multiple worlds, that the universe is constantly branching into incomprehensibly many versions. Critics ask where probabilities come from in many worlds. If both outcomes happen, why do we experience them with frequencies matching the Bohr rule, the 8-2 probability formula? Everett and subsequent defenders have developed decision-theoretic arguments, but debate continues about whether many worlds truly recovers standard quantum probabilities or requires additional postulates. Pilot wave theory, also called de Broglie-Bohm theory, or Bohmian mechanics, takes yet another route. Proposed initially by Louis de Broglie in 1927, and more fully developed by David Bohm in 1952, this interpretation says particles always have definite positions. The wave function is real and guides particle motion, but particles follow definite trajectories like in classical mechanics. The wave function evolves according to the Schrödinger equation. Particles move according to a guidance equation that depends on the wave function's shape. In regions where secant 2 is large, particles are guided to spend more time, reproducing the Bohr rule probabilistically. Measurement doesn't collapse the wave function. It just reveals where the particle was all along. This restores determinism in particle positions. Given initial positions and the wave function, future positions are determined. The randomness in quantum mechanics comes from uncertainty about initial positions, distributed according to Poiseuille's 2. Pilot wave theory is a hidden variable theory, with particle position being the hidden variable. The cost is non-locality. The guidance equation for one particle can depend instantaneously on the positions of distant particles through the wave function. This non-locality is explicit and unavoidable. Not just the non-locality of entanglement correlations, but actual instantaneous influence of one particle's position on another's velocity. Relativity isn't violated for signaling, but the underlying dynamics is non-local. Pilot wave theory also treats position as special. Momentum, energy, and other observables don't have definite values. Only position is real before measurement. Why position should be privileged is unclear. Some find this arbitrary, though defenders argue position is naturally special as the fundamental property that interacts with the environment. Objective collapse theories propose that wave function collapse is a real physical process that happens spontaneously without measurement. The Schrödinger equation is slightly wrong. In addition to deterministic evolution, there's a small random collapse term that occasionally makes the wave function jump to a definite state. The collapse rate depends on the system's size or complexity. For single particles, collapse is so rare it's undetectable. For macroscopic objects involving billions of atoms, collapse happens essentially continuously, preventing superpositions of different macroscopic configurations. This explains why we never see cats in superpositions of alive and dead. The GRW model, named after Ghirardi, Rimini, and Weber, who proposed it in 1986, specifies collapse mathematically. Each particle spontaneously localizes at a random rate, about once per 10^16 seconds. For a single particle, this is negligible. For a mole of particles, collapse happens constantly, keeping macroscopic objects in definite states. Objective collapse solves the measurement problem by making collapse physical rather than observer-dependent. It explains the quantum to classical transition naturally through spontaneous localization. But it modifies quantum mechanics, making testable predictions that differ slightly from standard theory. So far, experiments haven't detected these deviations, but they constrain the parameters of collapse models. Another approach is QBism, quantum Bayesianism, which treats quantum mechanics as fundamentally about agents making predictions rather than describing objective reality. The wave function represents an agent's subjective degrees of belief about future measurement outcomes. Measurement updates these beliefs, explaining collapse as Bayesian updating. QBism avoids many conceptual puzzles by not requiring the wave function to represent something physically real. Different agents can have different wave functions for the same system, just as they can have different probabilistic beliefs. But critics worry this makes physics too subjective, that it doesn't explain why agents with different wave functions nevertheless agree on measurement statistics. The consistent histories approach, developed by Robert Griffiths, Roland Omnes, and Murray Gell-Mann, assigns probabilities to entire histories of events rather than individual measurement outcomes. You can ask about the probability that a particle was at position A at time 1, then at position B at time 2, and so on, provided the history is consistent, meaning interference terms vanish. This framework allows discussion of events without measurement at every step, addressing the issue that Copenhagen seems to require constant observation. But determining which histories are consistent and which aren't involves subtle choices, and different choices can lead to different narratives about what happened. There are other interpretations, modal interpretations, relational interpretations, Neo-Copenhagen views, various flavors of ensemble interpretations. The landscape is complex and no interpretation has achieved consensus. This is not because physicists are confused about how to use quantum mechanics. Calculations are straightforward and predictions are clear. The interpretations disagree about ontology, about what exists and what the formalism represents. Some physicists take a pragmatic stance, saying interpretations don't matter if they make identical predictions. Learn the math. Calculate. Don't worry about what's really happening. This is sometimes called the shut up and calculate approach, though most physicists who hold this view are more thoughtful than the phrase suggests. Others argue interpretations matter deeply. They guide intuition, suggest new theories, and relate to fundamental questions about the nature of reality. The measurement problem points to something we don't understand, possibly a need for deeper theory. Dismissing interpretations might mean missing important clues. The situation is genuinely unusual in physics. With classical mechanics or relativity, we have a clear ontology. Particles have positions and velocities. Space-time has a metric. With quantum mechanics, the mathematical formalism is clear, but what it's telling us about reality remains genuinely disputed nearly a century later. Perhaps future developments will resolve this. Quantum gravity, a theory combining quantum mechanics and general relativity, might require modifications to quantum mechanics that clarify its interpretation. Or experiments might detect deviations from standard quantum mechanics, ruling out some interpretations. Or philosophical analysis might converge on one interpretation as superior. For now, we live with the puzzle. Quantum mechanics is spectacularly successful empirically, but conceptually mysterious. We can calculate anything we can measure, but we don't agree on what those calculations mean about the world. And that's where we'll leave the interpretations, unsolved but illuminating, showing that even our best physical theory contains deep questions about the nature of reality that remain genuinely open. Applications and the quantum future. For all its conceptual strangeness, quantum mechanics is not merely a philosophical puzzle. It's the foundation of modern technology. Without quantum mechanics, much of the 20th and 21st century would simply not exist. The device you might be listening to this on, the electricity powering it, the medical imaging that keeps people healthy, all depend on quantum effects. Start with semiconductors. In classical physics, materials are either conductors that allow electricity to flow easily or insulators that block it. Semiconductors, like silicon, fall in between, and their behavior can't be understood classically. Electrons in solids occupy energy bands, allowed ranges separated by forbidden gaps. Whether a material conducts depends on whether electrons can easily jump to higher bands, and this band structure emerges directly from quantum mechanics. Transistors, the building blocks of all modern electronics, exploit quantum properties of semiconductors. A transistor uses a small voltage to control a larger current, acting as a switch or amplifier. The first transistor was demonstrated at Bell Labs in 1947, and the inventors, Bardeen, Broglie, and Shockley, explicitly used quantum mechanics to design it. Integrated circuits pack millions or billions of transistors onto silicon chips smaller than a fingernail. Every computer, smartphone, and digital device relies on these quantum-engineered structures. The global semiconductor industry is worth hundreds of billions of dollars annually, all because quantum mechanics explains how electrons behave in crystals. Lasers are another quantum technology. The word laser stands for light amplification by stimulated emission of radiation, and that stimulated emission is a purely quantum phenomenon. Einstein predicted it in 1917 as part of his work on quantum transitions. An electron in an excited state can be stimulated to emit a photon by the presence of another photon with matching energy. The emitted photon is identical in frequency, phase, and direction to the stimulating photon. This creates coherent light, where all photons march in lockstep. Ordinary light from a bulb or the sun is incoherent, photons with random phases. Laser light maintains phase relationships, allowing interference effects and precise focusing. The first working laser was built in 1960, and lasers now appear everywhere. barcode scanners, fiber optic communication, laser pointers, DVD and Blu-ray players, surgery, industrial cutting, and scientific instruments. LEDs, light-emitting diodes, convert electricity directly into light through quantum transitions. Electrons recombine with holes in a semiconductor, dropping to lower energy states and emitting photons. The photon energy, and thus the color, depends on the band gap of the material. Quantum mechanics determines which materials produce which colors, enabling the full-spectrum LED lighting, now replacing incandescent and fluorescent bulbs worldwide. Solar cells work in reverse, absorbing photons and creating electron-hole pairs that generate electric current. Again, the efficiency and wavelength sensitivity depend on quantum properties of the semiconductor. Modern high-efficiency solar cells use multiple layers with different band gaps to capture more of the solar spectrum, all designed using quantum calculations. MRI, magnetic resonance imaging, exploits the quantum spin of atomic nuclei. Hydrogen nuclei in water and fat have spin that can be aligned with strong magnetic fields. Radio waves flip these spins, and detecting their relaxation back to alignment creates images of soft tissues. MRI revolutionized medical diagnosis, and it's fundamentally a quantum phenomenon involving nuclear spin states. Atomic clocks, the most precise timekeeping devices ever built, use quantum transitions in atoms. Cesium-133 atoms have a transition between two hyperfine states with a frequency of exactly 9,192,631,170 Hz. This defines the second. Modern optical atomic clocks using strontium or ytterbium are even more precise, losing less than 1 second over the age of the universe. GPS satellites carry atomic clocks, and GPS accuracy depends on quantum-precise timekeeping. Quantum chemistry, the application of quantum mechanics to molecular structure and reactions, guides drug design and materials development. Pharmaceutical companies use quantum calculations to predict how potential drugs will interact with target proteins. Materials scientists design new compounds with specific properties, from stronger alloys to better batteries, guided by quantum models of electron behavior. All of this already exists, using quantum mechanics understood in the 1920s and developed through the 20th century. But emerging quantum technologies promise to be even more transformative. Quantum computers exploit superposition and entanglement to perform certain calculations exponentially faster than classical computers. A classical bit is either 0 or 1. A qubit can be in a superposition of both. 2 qubits can be in superpositions of 0, 0, 9 and 10, and 11 simultaneously. N qubits can represent 2 n states simultaneously. This doesn't mean quantum computers are faster at everything. For many tasks, classical computers work fine, but for specific problems, searching unsorted databases, factoring large numbers, simulating quantum systems, quantum algorithms offer dramatic speedups. Shor's algorithm, developed by Peter Shor in 1994, can factor large numbers exponentially faster than the best-known classical algorithms. This threatens current encryption systems, which rely on factoring being hard. RSA encryption, used for secure Internet communication, would be broken by large-scale quantum computers. Fortunately, quantum computers also enable quantum cryptography, provably secure communication. Quantum key distribution uses entangled photons or single photons in superpositions to share encryption keys. Any attempt to intercept the key disturbs the quantum state, revealing eavesdropping. Systems are already deployed commercially, with quantum-secured fiber optic links connecting government facilities and financial institutions. Building quantum computers is extraordinarily difficult. Qubits must maintain quantum coherence, staying in superposition without collapsing to definite states. But the environment constantly threatens coherence through decoherence, unwanted interactions that destroy superpositions. Qubits must be isolated yet controllable, a delicate balance. Current quantum computers use various physical implementations. Superconducting circuits cooled to millikelvin temperatures, trapped ions held by electromagnetic fields, neutral atoms in optical lattices, nitrogen vacancy centers in diamond photonic circuits. Each approach has advantages and challenges. As of now, quantum computers with dozens to hundreds of qubits exist, but scaling to thousands or millions needed for practical applications remains challenging. Quantum simulation, using quantum computers to model other quantum systems, might be the first practical application. Quantum systems are exponentially hard to simulate classically because the state space grows exponentially with system size. But a quantum computer naturally represents quantum states, potentially simulating chemistry and materials at unprecedented accuracy. This could revolutionize drug discovery, allowing detailed simulation of how molecules interact with biological targets. It could enable design of better catalysts for industrial chemistry, more efficient solar cells, high-temperature superconductors, and materials with properties impossible to discover by trial and error. Quantum sensing exploits quantum effects to measure with extraordinary precision. Quantum sensors have already achieved remarkable sensitivity. Atomic gravimeters use quantum interference of atoms to measure gravitational acceleration with precision sufficient for detecting underground structures or monitoring volcanic activity. Quantum magnetometers detect magnetic fields weak enough for mapping brain activity. Quantum metrology, the science of measurement using quantum systems, approaches fundamental limits set by the Heisenberg uncertainty principle. Entangled states can exceed classical measurement precision, achieving what's called the Heisenberg limit rather than the standard quantum limit. This enables more precise clocks, better navigation systems, and more sensitive detectors for everything from gravitational waves to dark matter. Quantum biology, while still somewhat speculative, investigates whether quantum effects play functional roles in biological systems. Evidence suggests quantum coherence in photosynthesis, where energy transfer through light harvesting complexes might exploit quantum superposition for enhanced efficiency. Bird navigation might use quantum entanglement in radical pairs in their eyes to sense magnetic fields. Whether quantum effects are essential to these biological functions or just incidental remains debated. But even if quantum biology doesn't revolutionize our understanding of life, it demonstrates that quantum effects persist in warm, wet, noisy environments longer than once thought possible, which has implications for quantum technology development. Looking further ahead, quantum field theory, which extends quantum mechanics to incorporate relativity and describes fundamental particles and forces, might yield new technologies as it's better understood. The standard model of particle physics, our best description of fundamental reality, is entirely quantum mechanical. Understanding the Higgs field, dark matter, or physics beyond the standard model might eventually enable technologies we can't yet imagine. Quantum gravity, unifying quantum mechanics and general relativity, remains unsolved. Whether this requires modifying quantum mechanics, modifying relativity, or both is unknown. But the pursuit has already yielded insights about black holes, including Hawking radiation, a quantum effect where black holes slowly evaporate. Understanding quantum gravity might reveal whether space-time itself is fundamentally discrete or continuous, whether it emerges from deeper quantum structures. String theory and loop quantum gravity, leading approaches to quantum gravity, both suggest space-time has quantum properties. String theory proposes fundamental strings rather than point particles, with different vibration modes corresponding to different particles. Loop quantum gravity quantizes space-time geometry itself. Neither theory is yet experimentally verified, but both exemplify how quantum thinking extends beyond atomic scales to the fabric of reality itself. The quantum future is both promising and uncertain. Quantum computers might transform cryptography, optimization, and scientific simulation. Or they might remain specialized tools for specific problems, with classical computers handling most tasks. Quantum sensors will certainly improve measurement precision across many fields. Quantum communication might secure information networks against any eavesdropping. But predicting technology is notoriously difficult. Quantum mechanics itself was pure physics for decades before anyone imagined transistors or lasers. Many quantum technologies likely haven't been conceived yet. What seems certain is that quantum mechanics, despite its conceptual mysteries, will continue shaping technology and science for the foreseeable future. We live in a quantum universe. Everything, ultimately, follows quantum rules. Classical mechanics is an approximation that works when systems are large enough, and when quantum effects average out. But at the foundation, reality is quantum. Atoms are stable because of quantization. Chemistry works because of quantum bonding. Materials have their properties because of quantum statistics. Light interacts with matter through quantum transitions. Understanding quantum mechanics doesn't make the world less mysterious. If anything, it reveals deeper mysteries. But it's our best theory of nature, tested more precisely than any other, and it's given us both profound insights into reality and practical technologies that shape modern life. The quantum revolution that began with Planck's desperate hypothesis continues, and where it leads remains an open question. Living in a quantum world. We began with 3 problems that classical physics couldn't solve. Heated objects that should have incinerated everything around them but didn't. Light ejecting electrons in ways that made no sense if light was a wave. Atoms that should have collapsed in fractions of a second but stubbornly persisted for billions of years. Each problem seemed minor, a small cloud on the horizon of an otherwise complete physics. Each turned out to be a crack in the foundation. And when physicists followed those cracks, the entire edifice of classical physics came down, replaced by something stranger and more powerful than anyone had imagined. Quantum mechanics is now nearly a century old. The Schrödinger equation was written in 1926. The interpretational debates between Bohr and Einstein happened in the 1930s. Bell's theorem came in 1964. This isn't new physics anymore. It's established, tested, verified to extraordinary precision across countless experiments and applications. Yet, quantum mechanics remains counterintuitive. It violates our everyday expectation about how reality works. Objects don't have definite properties until measured. Particles behave as waves and waves as particles. Distant objects remain connected through entanglement. The act of observation affects what's observed. Measurement outcomes are fundamentally probabilistic. None of this matches our experience. We live in a world of definite objects with specific properties. Balls follow definite trajectories. Walls are solid barriers. Separated objects are independent. Observation reveals pre-existing properties. Randomness comes from ignorance, not fundamental indeterminacy. But our intuitions were built at human scales, where objects contain trillions of atoms and quantum effects average out. The classical world we experience is real, but it's an approximation. A limit of quantum mechanics that applies when systems are large and when we don't look too closely at individual particles. At atomic scales, quantum rules dominate. Electrons in atoms occupy discrete energy levels. Chemical bonds form through quantum overlaps of electron wave functions. Photons are emitted and absorbed in quantum jumps. Tunneling allows particles to pass through classically impenetrable barriers. None of this makes sense classically. All of it is verified experimentally. The conceptual puzzles remain. We don't agree on what the wave function represents. We don't know what causes collapse, or if collapse actually happens. We don't understand why we see definite outcomes when quantum mechanics describes superpositions. The measurement problem is unsolved. Multiple interpretations exist, each internally consistent but radically different in what they say about reality. This might seem like a failure, a theory incomplete after a century. But perhaps it's better understood as a sign that quantum mechanics is pointing towards something deeper about nature that we haven't fully grasped. The formalism works perfectly. The predictions are spectacularly accurate. What remains unclear is the ontology, what exists and how it relates to our observations. Some physicists believe future developments will clarify this. Quantum gravity might require modifications to quantum mechanics that resolve interpretational issues. Experiments might detect deviations from standard predictions that rule out certain interpretations. Or mathematical advances might reveal structure in quantum mechanics that makes one interpretation obviously correct. Others think the interpretational ambiguity is permanent, that quantum mechanics describes correlations between observations without specifying an underlying reality, that trying to go beyond what can be measured is inherently problematic. This isn't defeatism. It's recognizing that physics describes what we can observe and predict, and reality might not neatly separate into observed and unobserved parts the way classical thinking assumes. What's remarkable is that despite these conceptual puzzles, quantum mechanics has given us both profound scientific insights and transformative technologies. We understand atomic structure, chemical bonding, the behavior of materials, the fusion processes in stars, all through quantum mechanics. We've built semiconductors, lasers, LEDs, atomic clocks, MRI machines, solar cells, technologies that shape modern life. And we're at the beginning of a second quantum revolution. The first revolution, in the 20th century, used quantum mechanics to understand nature and engineer materials and devices. the second revolution, happening now, exploits distinctly quantum effects like superposition and entanglement for computation, communication, and sensing. Quantum computers, quantum cryptography, quantum sensors, quantum networks represent a new technological frontier. Whether they'll be as transformative as transistors and lasers remains to be seen. But they demonstrate that quantum mechanics, even its strangest features, can be harnessed for practical purposes. Living in a quantum world means accepting that reality at its most fundamental level doesn't work the way our intuitions expect. It's not that particles are tiny balls that sometimes act wavy, or that waves are disturbances that sometimes act particle-like. These classical pictures don't work. Quantum objects are something else, something that exhibits wave-like behavior in some contexts and particle-like behavior in others, but is fundamentally neither. It means accepting non-locality. Entangled particles remain connected regardless of distance in ways that can't be explained by local interactions or pre-existing properties. Space-like separated measurements are correlated more strongly than any local theory allows. The universe is not made of independent parts that interact only through local forces. Quantum mechanics shows that separateness is less fundamental than classical physics assumed. It means accepting uncertainty. Not just that we can't measure position and momentum simultaneously, but that particles don't have simultaneous definite values for both. The uncertainty principle isn't a measurement limitation. It's a statement about what properties quantum systems possess. Reality at small scales is fundamentally indefinite in ways that classical physics never imagined. It means accepting superposition. Before measurement, particles exist in combinations of states that seem mutually exclusive classically. Not that they're in one state or another, and we don't know which, but that they're genuinely in superposition, with physical consequences like interference that depend on both components being present simultaneously. And it means accepting that we don't fully understand measurement. Why measurement outcomes are definite when quantum mechanics describes superpositions remains puzzling. The interpretations offer different answers, but no consensus has emerged. This is uncomfortable, but it's honest. The measurement problem is real and unsolved. Does this mean quantum mechanics is incomplete, as Einstein believed? Bell's theorem rules out local hidden variables, the kind of completion Einstein wanted. But perhaps there's some other completion, non-local variables or modifications to quantum mechanics that preserve its predictions while clarifying its meaning. Or perhaps quantum mechanics is complete. And the puzzlement comes from trying to impose classical concepts on a fundamentally non-classical reality. What shouldn't be done is to confuse quantum mechanics with mysticism. The theory is mathematically precise and empirically tested. It doesn't validate consciousness creates reality philosophies or justify vague invocations of quantum healing or quantum manifestation. Measurement in quantum mechanics means physical interaction, not conscious observation. Superposition describes mathematical combinations of quantum states, not metaphysical states of being. The strangeness of quantum mechanics is real strangeness, documented in experiments and calculations, not metaphorical or open to arbitrary interpretation. It's strange in specific, well-defined ways. Respecting that specificity means not co-opting quantum language for non-quantum purposes. If there's a lesson from quantum mechanics beyond the physics itself, it's perhaps about the relationship between theory and reality. Classical physics encouraged the view that theories describe an objective reality existing independently of observation. Quantum mechanics challenges this, not by making everything subjective, but by showing that what can be observed and what exists independently might not separate cleanly. Different interpretations navigate this differently. Copenhagen says only measurements are real. Many worlds says everything is real, including all branches. Pilot waves say particle positions are real and the wave function guides them. Each trades different forms of strangeness, and none has one consensus. Living with this ambiguity, working with a theory we can't fully interpret, has been the situation in physics for a century. It's uncomfortable, but also productive. Quantum mechanics continues to reveal new phenomena, enable new technologies, and inspire new questions. The lack of interpretational consensus hasn't prevented progress. If anything, the open questions drive research. So we end where we began, with mystery. Not the mystery of ignorance, but the mystery of knowing a great deal while recognizing how much remains unclear. Quantum mechanics is humanity's most successful scientific theory, and our most puzzling. It describes reality with unparalleled precision, while leaving fundamental questions about that reality unanswered. Perhaps future generations will look back at our interpretational confusion the way we look back at 19th century debates about the ether, as a conceptual muddle that evaporated once the right framework emerged. Or perhaps the ambiguity is permanent, reflecting genuine limits on what can be known or said about underlying reality. Either way, quantum mechanics stands as one of humanity's great intellectual achievements. In less than 3 decades, from Planck's desperate hypothesis in 1900 to the Schrödinger equation in 1926, physicists overturned centuries of classical thinking and built a new framework that describes the microscopic world. That framework has been tested, refined, and applied for nearly a century since, never failing, always surprising, perpetually strange. The quantum world is the real world. Everything is quantum at its foundation. We live in superposition, entanglement, and uncertainty, even if we don't directly perceive them. Quantum mechanics reminds us that reality is richer, stranger, and more subtle than everyday experience suggests. And that's a fitting place to end, with wonder at the universe's quantum nature and appreciation for the human ingenuity that revealed it.